from USP, who is gonna give us a tutorial on solid-state spin qubits at room temperature. Okay. Thank you, Sergio.
Okay, can you hear me? Okay, good. So, good morning, everyone. It's a great pleasure to be here today. And of course, I need to thank the organizers, particularly Thaisa, for putting it all together and giving me the opportunity to be here. I was attending the first workshop in Brazil, in São Carlos. At the time, I was essentially an outsider, and it was the time that I was learning about these things. I was very excited and interested in the kind of experiments and topics of this conference. So it's very nice to be here today, talking to you about some of the things we've been doing in São Carlos. So let me check if this is working. Okay, it is. With NV centers, but I was in charge of giving a tutorial on the subject, just like the previous tutorials in NMR in the first days of the conference. I decided to give a more open general topic. So I put here not just focusing on NV centers, and I even had prepared something for 2D materials to set the stage for Carmen, but she did such a wonderful job yesterday that I think it's not necessary. If you happen to miss that, you should go and see the presentation on the YouTube. So I will be actually mostly talking about NV centers in diamond. So NV centers are spin optically active defects that have spin, and my goal today here is mostly really give you a tutorial in the basics. So most of my time will be talking about how the things work. But this is a very broad field. I mean, I just picked some random papers here. In this case, I'm getting too used to the control yet. So mostly focusing on the qubit part. It's been more than 20 years, around 20 years or so, over 2 decades now, this field with the NV centers as we know them today. It turns out the color centers, like the NV centers, have been studied for longer, but the particular properties that we are exploiting here are more recent. So it's a very wide topic, and for the interest of this presentation, I'll be mostly focusing on the essentials, meaning I'll talk quite a bit about the photophysics and the ODMR, or optically detected magnetic resonance, which is the main tool that is used. Carmen alluded and talked about that yesterday as well. So here I will go into the details. Then I want to focus give you a complete example using magnetometry. As I will mention later, there are other applications, many other applications. And I will start that building up from the classic picture, and so you will understand how it, sorry, still getting used to this thing here. And then, but I want to connect with the qubit part, which is the part that is arguably the most interesting part for many of the applications, current applications, and particularly for this community. So I will draw an analogy and a connection with the spins in nuclear spins that you heard about in the first tutorial sessions. And then I'll talk about how one can control, characterize those qubits. And sorry, again. And then I'll talk a little bit about some applications that we've been exploiting in São Carlos. And far in the end, if I have still time, I will mention briefly, basically just flash some results, new results, preliminary results that we had. That's not the main topic, but I think it's probably interesting. Maybe some of you later might be interested in talking. So let's get started. So the NV center is, sorry. So the NV center is a point defect in the diamond lattice. So the idea is you have a substitutional, you have a substitution of a carbon atom by a nitrogen atom, and you have a nearby vacancy. So this pair, the electronic orbitals, and so work as pretty much like an artificial atom. I mean, it's funny to say that way because there are lots of atoms here. But what I mean is that within the band gap of the semiconductor, you have actually transitions line like you would have for an atom. And the NV center borrow a lot of nice properties actually from the host material, that diamond. So diamond has a lot of interesting properties that are mentioned here, but I think it's not worth going into the details. But essentially, it has the interaction with the phonons is such that the coherence time in this system, even at room temperature, is very long. I'll talk a little bit about that and how we characterize it. And another important feature is that it has a strong optical dipole transition in the visible, which makes it very efficient for detection. So it means that you can see quite easily just a single spin defect in the material. So for a lot of the applications I'll be talking here today, I'll be actually talking about an ensemble. But the same physics and principles apply even if you're working with a single NV center. So you can actually control the spins of a single electron in a material and see it very easily using optics. So this is sort of the bottom line of the main features of this defect. So a little more detail. So you have here the vacancy and the nitrogen. The diamond has this tetrahedral structure, of course. The bounding distance, the distance between the atoms is in the order of 0.15 nanometers. And another important thing is that I'll be saying NV all the time, but there are actually at least two types of NV defects. The neutral NV, NV0, and the NV, the charge that has an extra electron that's trapped in this configuration here. So the one that is most interesting for the applications, particularly the one that I will be mentioning here, is the NV minus. So every time I say NV, I'll be referring to NV minus. But it's actually important to understand the role of NV0. And maybe I'll mention a little bit about that more later. All right, so I'll be focusing on NV minus. From now on, I'll be saying just NV. The overall picture is, this is not in scale, of course, but this is the band gap. The diamond has a very wide band gap. So a pure diamond is completely transparent. The energy to do an optical transition here is 5.5 electron volts. So it's in DUV, deep UV. But the defect, the NV center defect, have this atom-like structure that's within the band gap. And here's the relevant transitions, optical transitions. As many of the applications I will mention later, we will be actually dealing with the spin. So it's another energy scale that I'll show you in a little bit. And just actually, just the wrong way. So here is the emission spectra at room temperature for the NV center. So let me show you a little bit more detail here. So the bigger line, this one here, this is for an ensemble, measuring an ensemble, meaning several NV centers. In this case, the excitation is in 532 nanometers. So you have this very broad, several hundred nanometers wide emission with these feature lines here, which are the zero phonon line in this case here, this 637 nanometer transition is the zero phonon line for the NV minus. And the 575 nanometers is the zero phonon line for the defect NV0. So here you're actually seeing both lines. Here's a comparison. This is the ensemble. And this one here is for a single NV center. And from this peak, you can figure that this is the NV minus. It happens to be the one that I was looking at in this case here is the NV minus. There is a rich process of photoionization that happens, and you can actually have this cycling and even controlling to enhance your signal to noise. But I'm not going to go into the technical details about these things, just to mention it. All right, so the relevant part for the applications actually turns out to be the spin part of the NV center. So the optical part is, as we will see later, is just basically to prepare the system and to read it out. So the things that we'll be looking at here for qubits or even sensing will be dealing with the spin, the electron spin, the spin of the electron, this minus charge that is trapped in the NV center. Okay, so for that, at zero field, the ground state for the NV minus or NV center is a triplet. So it means that you have and the levels are the degeneracy here is broken. So you have a separation of characteristic separation of 2.87 gigahertz between MS0 and plus or minus 1. And just to give you, to set the scale, this corresponds to about a tenth or 12 micron electron volt, just to give you an idea. So here we have electron volts, optical transitions. Here we're talking about micro electron volts. That means that at room temperature, these levels are mostly equally occupied. You don't have spin polarization in the system at room temperature. So this is the energy, the thermal energy at room temperature. So, but as we will see later, the features, the characteristics of the transitions are such that you have a very efficient optical pumping process that happens just by shining this 532 light. In a little while, you basically pump all the populations of these states here to the zero states. So you initialize your system, your qubit, if you wish. And that has to do with this, with the photophysics, basically the times of the excited states and the probability of transition for this state, for this singlet state here. Carmen yesterday mentioned how that works. I'm just giving a little bit more detail here. Basically, what happens is the optical transitions here has to preserve the spin. The dipole optical transition has to preserve the spins. So 0 goes to 0. So the excited state is also a triplet. So 0 goes to 0, 1 to 1, and so on and so forth. But there's a stronger probability if you are in this. If you are in the plus or minus 1 states, the probability to do this inter-system crossing is much higher. And that process leads to, this happens for, is non-radiative process. So sorry, pressing the wrong button here all the time. Sorry about that. So the optical transition here, the lifetime is about 13 nanoseconds, 15 nanoseconds or so. And if you happen to go to this state, the state has some much longer time. So it shelves this state. And actually, in the end, after several cycles, you have the system going to the ground state. So that will happen for a single NV. We spend most of the time in the 0 state. And if you have an ensemble, basically all, not all, but most of the defects in the ensemble will go to the 0 state. Okay, so this is the initialization process. What that means is what Carmen mentioned yesterday for the HBN, and so same process, similar process. What happens is because of this difference in these transition rates, if you wish, you end up having the population here, but also means that depending on the spin state that you are, the fluorescence will change on time. If you keep the laser on for a long time, it eventually will have a stationary state, and there's no difference in the fluorescence anymore. But if you do the timing just right, you can actually detect differences in the photoluminescence that depends on the spin. So that's basically the idea. That's how you use and read the spin state using the photon. Okay, so this leads to what is called the optically detected magnetic resonance, ODMR for short, which means that if you, after you have a stationary state, say, that after turning on the 532 lights for a while, you have a given amount of fluorescence or photoluminescence, or PL for short. And if you now scan the microwave, eventually you will hit the resonance here. And when you do that, then you have an alternative path, and you do the transition from some of these effects or atoms, or artificial atoms, or the NV centers that you have. We'll go to this state. So from that, it goes to here, spend a longer time here, which means that the fluorescence signal will drop a little bit. So this decrease in the photoluminescence gives you the signature of the detection of the resonance. If you have no external field applied, you see that around 287 gigahertz. And of course, if you apply a magnetic field, then you will have a Zeeman shift of these levels, and you will see two transitions. Here is just the detail for the transition lines. And if you now apply an external field, you Zeeman shift those plus or minus levels, and then you will see two peaks. And the separation of two peaks give the field that is being applied to the center. I'll get a little more, I'll give a little more detail how that works. So that's actually the feature that we'll use to measure the magnetic field. I'm gonna borrow this image here, a nice image here, just to understand it a little better. So here are the levels that we talked about. Again, the spin levels here are very, very tiny compared to the optical transition here. And the NV center, the direction that connects the defect, the vacancy to the nitrogen is the axis, defines the axis of the NV center. And the field that the splitting here, the Zeeman shift, will depends on the field that is parallel to the axis of the NV center. So if you have, say, a Z field, a field, say, in this direction here, with regard to the NV center, is just the projection of this field along the axis direction that we call the shift. And using that, you can detect actually what the external field is, right? So let's now understand a little better how this allows you to make an optical vector magnetometer. By that, I mean, if you have an ensemble in a pure crystal, you have 4 possible orientations for the direction of the axis of the NV center. You can have, for whatever orientation of your crystal, you have just 4 directions that the NV defect can be aligned. And for each of these directions, for a given external field, you have an angle and a different Zeeman shift. So if you align things right, usually we apply a bias field to break the degeneracy of the levels. For this case, you can have up to 8 levels, 2 for each of the directions of the NV centers. And this is basically what you use by doing the spectroscopy of these levels and the shifts. You can assign each pair to each direction, and you know the orientation of your crystal. You actually know what is the vector magnetic field, local magnetic field for a given defect or for the ensemble by doing the spectroscopy, the microwave spectroscopy, like I'm showing here. Here's actually a experimental data from the lab, and I color-coded them for each of the axes and the directions here. So that's what I was saying. By looking at this, each pair here corresponds to the shifts, the Zeeman shifts of the fields along one of the 4 directions. All right, so a little bit about the experimental stuff. I will describe our setup. So here's a detailed view, a simplified schematic view of the system. I'll show you some pictures later for the actual setup. So basically, we have here a laser, the 532 laser, an acousto-optic modulator just to turn on and off the laser, and it will be imported for certain protocols as well. Some optics to focus the light into the diamond. We have the microscope objective. In our case, is a home-built setup. Here you see an image for the laser and so on. And here is actually the sample. I'll show you a little more detail. The part that you most likely not seeing here, there's a square here that is the sample. So I'll blow it up for you. So in this part here, you have the diamond chip. It's 2 by 2 millimeters size, and it has, in this case, has a thickness of about 200 micrometers. Just so you understand the next slides, we have here the microwave line. So here provides the microwave field, and here we have just a test line where we pass a direct current, the DC current here passing through this wire. This works just like a thin wire just for calibration purpose. I'll show you a little bit more that in the detail. What you need to understand is actually the geometry of the sensor. So the sensor is, as I showed you before, here. But in one of these surfaces, on the top of the surfaces, was implanted the NVs, the nitrogen and the NV centers were produced at very, very close to the surface, one of the surfaces of the crystal. So for this sample here, it turns out that the depth of the NV layer is about between 10 and 20 nanometers from the surface. The thickness of the layer is just a few nanometers in this case. And the diamond chip itself is much thicker. This thickness here is something that we control depending on the experiments and the optics and the microscopes. And I'm not going to bother you with the details, but it's relevant for the actual experiments. But what you need to know is that the NV layer is very, very close to the surface, which means that it makes it very sensitive to whatever you put in the surface. So for 2D materials or things that has this geometry, it makes a very, very sensitive sensor, as I will describe later. Okay, so that's basically what the sensor is for this setup. So what we do is we focus the light in a certain region, and that again would depend on the experiment or the purpose of the application that you're designing. For what I'm going to show you here, we will not actually focus the beam. I will have it slightly misaligned, if you wish. I mean, not just actually parallel when it gets to the objective. So it will illuminate a bigger spot. So I can make a wider image, I mean, a larger image. And here's actually the PL, the photoluminescence that we see on the camera. This is an image on a CCD camera. And here, for each pixel in the image, when we do the scanning of the microwave, like I described before, we can analyze now for each pixel of that image, we get the spectra for each pixel. That means that I can now compare the positions of the peaks for each pixel, and I determine, therefore, the magnetic field, the local magnetic field, the vector magnetic field in each voxel, in each pixel of the image. So that's basically how this so-called diamond microscope or NV microscope works for magnetometry. All right? So that's basically the main idea here. Here, using this process, these ideas, doing a lot of processing of the data after the collection, we can build these maps like this. This is the B, X, Y, and Z field, the vector of the magnetic field in each position of the NV center, or in that image that I showed you. Here's actually the PL image, the photoluminescence image. Here is a wide field microscopy of that line that was supposed to be a thin wire, but when you blow it up, you see that it's far from perfect. But basically, you have here a metal. So you have a current, electrical current going through here. This is the magnetic field produced in the regions around it. And this is the magnitude of the magnetic field. And actually, if you work things out, you can, of course, invert the information. And based on the fact that you have a fixed distance from the source to the NV layer, you can actually calculate the J, the density, the vector density current that is flowing through your circuit. So we did that for Charlie's PhD. This is one of the contributions for his PhD, and that was basically one of the first things we did in São Carlos, still in, I think, around 2018. And this was we have some papers on that, but this was not new. We actually was inspired by this work that was published just a year before. Then basically when we were starting the lab, where these authors use actually this idea, to map the density currents of a graphene layer sheet, basically using the same principles. So our case is much simpler, modest, but it's basically the same idea. We use that as a test bed to learn, to the processing, to calibration, and so on. So that's why we use that simple circuit. All right. So this is a quantum sensor, but this measurement process is not a quantum process. I call it a classical measurement. The measurement is classical. It's basically spectroscopy, microwave spectroscopy. What I mean by that is I'm not using a quantum protocol to do the actual measurement of the magnetic field, but I could, because the sensor itself is quantum. So instead of doing the measurements like I described, you could actually do, for instance, use a single NV center if you want, or even if you had an ensemble, you could do like post-process. And like this sketch here, there are lots of papers that describe this. There are actually several algorithms that you can use depending on the application. But this here gives you an idea. In this case here, you have the light that caused the spin polarization that I described. So you initialize the system, then you come with a sequence with pulse, like Carmen showed us yesterday, and Alexandre and Roberto also mentioned that the same ideas that you can do for the circuits for the NMR, same sequences, and you can use that, for instance, to build up the phase that you would get during the pulse. And there are many ways that you can process and get information about this. All right, so a little bit about how NV center sensors stand on the overall picture of the magnetometry sensors. This is, I actually saw, I apologize, this is an actually somewhat outdated image. I mean, it probably ends around here, maybe a little later, around the time. I think it's probably produced for the Charlie's thesis. But anyway, it's just to give you an overall picture to say that the NV centers are not usually the most sensitive sensors. You can, depending on the setup, if you use atoms or even squids, you can have more sensitive probes, but they are I'm doing. So maybe the battery. Trocar. Okay. Okay. I'll see. I'll get it here. So the message here is the following. The NV centers are in their own category when you compare sensitivity and size of the sensors. So the NV centers are capable of detecting a single spin because it can be as close as it gets to an atom or a molecule, for instance, which means that you can make very small sensors, or in other ways, another way of saying that you have a very high spatial resolution combined with a fairly good sensitivity. And again, it will depend if you use a single NV center or if you use an ensemble, the figures will change, but they're sort of in their own category with that respect. I have another ways of showing this here. This is again a bit old. I think these numbers here might be a little off from the state of the art today, but they give you the idea. And what I meant to convey in this slide is that the NV centers are not just magnetic sensors, not just for magnetometry. You can actually use other terms that you have in the Hamiltonian. And here I'm showing you the effective Hamiltonian for quote ground state. Or what I mean is I'm just describing here the spin Hamiltonian and just part of it, because it can be more complicated than that. But here are the most relevant terms for what we're talking here. So this is the zero field terms, the terms that depends on the sigma x and y and the z. This is the term here that is the separation of the splitting, the 2.87 gigahertz. And here is the Zeeman part of the Hamiltonian that senses the external magnetic field. And here is the coupling for the electron spin. And this is the nuclear spin. So these are the shifts that you can have for the nuclear part and the electronic part. And there are other terms. The one that I will mention here is the hyperfine interaction, which means that is the interaction that you have between the spin of the electron with the spin of the nucleus. It's relevant for what I'm going to say later. But you actually can use the NV centers to detect temperature. Some of these parameters are temperature dependent, so you can detect temperature as well. Pressure, as if you apply force, it changes the lattice parameters of the crystal, and things will shift a little bit, and so on and so forth. So you actually you can also detect electric fields, although the coupling with electric fields is much smaller than the magnetic one, and so on. This is a more current version that actually just a review of modern physics that was published just this year, that actually focus on the use of NV centers to detect signals, a magnetic resonance actually of single molecules. So here's the reference, and I recommend that you look at it later. It's a very nice one, has a lot of details, and it has current data, and actually shows this sort of same thing that I was showing before, but in a different way. Here shows the sensor distance, the distance from the sensor to the number of protons, meaning nuclei, nuclear spins, and the number of electrons if you have a paramagnetic sample, and so on, so forth. The thing that I think is interesting to note here is this is one, I mean this is one proton, one atom, hydrogen atom, if you wish, or one spin for the nucleus. Here is one for the electron. Here's the distances. So here we're talking about tenths or below nanometers or tenths of nanometers. And here, in other words, if you come here, you're detecting single nuclei at distances on the order of a nanometer or even below. And another thing that I think it's interesting to mention, this is the NMR signal detected through NV centers, the interaction with the nuclear spins around it. And this is the chemical shift that produces that. And for the specialists and NMR specialists here, the message is, it will depend on the coupling and the distances and so on, but you can, with the proper technique, you can actually detect something which is in the order of millihertz, which makes it sensitive to chemical shifts, basically allows you to detect the differences in molecules. You can use it, not quite yet to the same level of precision that NMR, but you can operate in a limit that regular NMR cannot. So you can actually detect a single molecule with the system, whereas for NMR, you need 10 to the 15 or something on that orders of molecules to provide you enough signal to detect in a NMR spectrometer. So this is the message. If you want to study the dynamics of single molecules or few molecules, or detect things that are very, very small, like study 2D materials or other exotic materials that has applications for quantum technologies, this is a sensor that is very useful for that kind of system. Again, in that review, there's a lot of applications. I just borrowed this image here just to give an example of some of them. I already mentioned them. So you can detect single molecules, simplified here, like a molecule on the top of the diamond. Study 2D materials and so on and so forth. I'm gonna go ahead. I still have some other things I want to mention. So I will now focus on the qubit part of this system. So you remember the Audemars spectra that I showed you before. So these are the peaks. If you set your frequency in one of these peaks, you set up your qubit, right? So you connect two levels. You have a two-level system, a qubit, and you can do the experiments like you pretty much can do with any qubit. You can detect, measure the coherence time, and so on. This is actual data for our sample. And so I'm gonna go a little bit more about how these things works. Going back here to this previous diagram. Now we're just talking about connecting two of these levels. You can choose which one you want, depending on the signal, applications, whatever. And basically, we will see just the Rabi oscillations between these two levels. So here, there's another piece of information which I think is relevant for you. So the NV center, here is the NV center, the vacancy, the nitrogen atom. But even if you have a perfect diamond crystal, once in a while you have a carbon-13. Carbon-12 doesn't have nuclear spin, but carbon-13 does have. And the natural abundance of carbon-13 is about 1%, a little more over 1%, which means that every 100 atoms, carbon atoms in the crystal, you have in average 1 carbon-13. So if you do the math, it turns out that is not, it's a fair amount. And that actually will determine some of the coherence properties of the NV centers, because these spins are typically uncorrelated, like Carmen said yesterday, but they produce a background noise that will cause the coherence. There are ways of dealing with that. Carmen already showed us how to do using this spin decoupling, so-called dynamic decoupling mechanisms. And I'm mentioning a few of them later here today. But what I want to emphasize here is that for the NV center, you have, say, an electron around here, and this electron is always interacting with this nitrogen atom. And the nitrogen atom, either the nitrogen 14 or 15, both have spins, nuclear spins, I mean. So this will cause the hyperfine interaction that I mentioned before. And this is by far the strongest coupling that you have around. But this carbon-13 around here will also do hyperfine interaction with the NV center, with the electron of the NV center. And depending on the distance that it is from the center, we'll have different couplings. I put it here mostly to give you on the scale. So for the nitrogen is around 3 megahertz. The near the close carbon here is a fraction of that, and so on and so forth. If you look the nitrogen here, you will see a splitting of the level. So this is the level that I showed before. For nitrogen 13 and 14, we'll have more levels due to this hyperfine interaction. And this actually show up in the data. If you do the processing, and you can actually extract this information. Here's an older paper that exploit this for some applications. And actually in our data, it actually shows up as well. Here I'm showing you a plot where we see the effect of the power broadening, I mean the intensity of the light, the laser light, on the effect of the line width of the resonance, Udemar resonance. If you look carefully here, you see that the separation here is basically the separation due to the nitrogen and those that the line. Here you see a blow-up image of the setup. Here actually the sample and the microscope that you have. This is a regular camera. I'm using this here just to show you that in this case here, we actually doing a fair amount of processing of this data to deal with the noise. But this is a regular CCD camera. This is not a fancy amplified, cooled CCD, nothing special. It's not photo counter or anything like this. This provides us this wide field imaging. And what we have for each pixel here is actually, because we're dealing with an ensemble, we actually have for each voxel, each pixel of the image actually has hundreds of NV centers in that region. So I'm seeing an average qubit, if you wish, in this case. But of course, I could be working in the limit that I have single NV centers. For that, I would need a different camera. And most likely, like most of the experiments, actually do photo counter. But this is a technical detail. It's relevant for the application, but the physics is basically the same. Okay, so in this case here, I'm just giving you the details. For this particular setup, the magnification that we have is such that each pixel here corresponds to something around 250 nanometers. And we had to develop our own protocol to do the processing of the images. I'm not going to go into the details, but just in simple terms, is we provide a sequence that do the polarization, in applying the microwave, and then those the proper calibrate to have a reference for the background, another reference for the luminescence without the microwaves, and doing the processing of this data, we get the information that I showed you before, and some of the information that I'll show you now. So this here looks a lot like the pictures like Roberto or Alexandre would show you for an experiment of NMR, with the exception that the NMR, usually because of the interaction of the dipole, has a much longer coherence time, like they described for chloroform, these seconds or minutes, even at room temperature. For the NV, this is much shorter, but here we're seeing a coherence time. This is a Rabi oscillation damped because of the coherence. So here, basically, what you're seeing is something related to the T2 time, the transversal coherence time. And this is basically a Rabi sequence. I mean, as oscillation, you set the laser and then you apply the microwave. And during the coherence time, you see the Rabi oscillations for the signal after all the processing. We're actually dealing always with the fluorescence and doing the processing like I described earlier. But we can build this information this way here. This is basically the Rabi period, in this case here, the pi pulse. And then you can apply whatever sequence, control sequence or protocol that you want. Here, I'm showing a sequence using the Ramsey sequence, using the same setup, just doing the processing accordingly and changing the pulse sequence. Here's the echo Han sequence. And I put here an image from Wikipedia just to explain basically the main idea. If you didn't get yet from Carmi's talk yesterday, or Roberto and Alexandre's, they also mentioned that for some of that for NMR. This actually was invented by the NMR people. This was invented in the 50s, Irving Hahn. But the idea here is basically you reverse, sorry, get back here. For some of you, the order of the x's here will be different, but it doesn't matter. Here's this 0 state. This is the 1 state of the qubit, which would be the state 0 or 1, depending on how you prepared. You give a pulse, a pi/2 pulse, which put the spins on the plane. But because each spin you have an ensemble, because each spin now will feel a different field, it will have its own alarm of frequency, which will cause decoherence. Basically, that's what you see. And so the measurement that you are seeing there is not actually the T2, is actually called the T2 prime, T2 star, which is the inhomogeneously broadened, or the fact that you have each spins, each NV center feels a different local magnetic field. But the Echo-Hahn sequence actually allow you to refocus it using this pi pulse here in the middle, so they start to fan out, and then you do the pi pulse here in the middle, and it will revert it. That's actually the picture showing, and then it will refocus. In the case of the NMR, that actually produce an echo signal in the coil. They actually use physical coils and detect that by induction. That's why you need a lot of spins to produce enough signal to detect in the coil. But the NV center you can detect in the single spin, but you cannot detect an induction signal. You have to detect it optically. So the protocol is different, and basically for the Hahn echo sequence, we need to add this extra pulse here to rotate the spins around the Z direction again. A technical detail, but is a difference if you look at the protocols in NMR for the NV centers. This is one of the changes that you need to do. But this is basically the idea. So if you do this properly, you would be expecting a signal like this. This would be the correct T2 time. We tried to do that in our sample, and when we did, we actually saw this. And remember, we're still learning. I mean, we're learning as we go. I was puzzled by that at first, but it didn't take much to notice that the separation here corresponds to the hyperfine. So this is basically a modulation caused by the hyperfine interaction with the nuclei from the nitrogen. So we can actually detect that very easily in our case. And then if you borrow, I mean, this is the explanation that I was referring to, that I mentioned before. So if you borrow the knowledge, wide knowledge from the NMR and EPR people, because this is effectively EPR, I'm doing the spectroscopy, the signal of the electron here. So EPR, for this community, I need to clarify, is not the EPR paradox, is the electroparamagnetic resonance, or ESR, if you prefer, electron spin, ESR, electrons resonance. But anyway, so if you model it properly, you can actually use these given protocols and get the information. The Echo-Hahn sequence is actually also called by the SN2 pulse sequence, and SN means electron spin echo envelope modulation. Here I show a more elaborate sequence, this 3-pulse sequence, which actually decouple that sequence here and allows us to extract these parameters here with more precision. So if we do this sequence, we actually get here with a fairly good precision the coupling with the nitrogen, and this here is actually the Larmor frequency of the nucleus, which you can actually compare to the local magnetic field. So in the case of the hyperfine, we have like a kilohertz resolution and tens of hertz resolution for the nuclei, for the nucleus. So anyway, so using this wide range of methods, we can actually apply methods like using relaxometry, using the relaxation time, like people do in NMR. In this case here, doing an image. So this is a spin map, a 2D map of the coherence for the sample. This is actually from the own sample and mostly reflect the inhomogeneity of our coil. I'm almost done. So basically this is basically what I want to show you for the basics. We just flash you some results, and those of you interested can talk to us later. So here I'm showing you some preliminary results that we're seeing here at CBPF, actually using now a different method, an all-optical detection of the magnetic structures. Depending on what you want to study, the local fields may be so strong that the ODMR signal goes to 0. This is a way of going around it. And what you're seeing here are skyrmions. So we're actually probing materials, a 2D material, not exactly a 2D material in the same sense that Carmen mentioned today, but a heterostructure of layers of magnetic material that break the symmetry and create these skyrmions at room temperature. And here what you're seeing are images imprinted in the NV luminescence that give you information about the skyrmions. Here is basically the same setup, except that it's been shorter, and this sensor is it has an extra feature that has a thicker layer here, an rich layer of carbon-12, which means that the spin coherence here is larger. So the NV layer is embedded within this enriched layer here of carbon-12, which means that the spin coherence will be larger in this case. Here another image just to show you some of these features of the skyrmions. This here is, we believe it's a pair, a skyrmion pair. And what you're seeing here is an image of the luminescence around this. So you see that one part it goes down, the other goes up. So this reflects the directions of the local magnetic field. Here are, perhaps we're still studying that and learning exactly how to analyze, but this here is, we believe that might be actually charge, higher topological charge skyrmion. As I said, I don't have time to explain, but you can go and chat with us later. Me, Alexandre, we can discuss the details. This is a work that hopefully will be in a few weeks in the archives. Is a description of a thermodynamic description of the optical pumping process. So this is a collaboration with Ivan Medina and Diogo. So you can also talk to us later. We can define analytically the heat work and heat flow and so on, and you can calculate that based on the pulsing. And this is just for the optical part, something similar to what Marcelo was saying, mentioning in his first talk. Here, just to finish this, the same lab, I have an optical tweezer lab. We actually did experiments trapping NV center nanodiamonds with NV centers optically. And in this setup, we actually also doing stochastic thermodynamics, classical stochastic thermodynamics for Brownian particles. Here, Stalita finished her PhD the beginning of the year. We studied some optical protocol here, as prescribed and described by Cypher, Schmidt, and Cypher quite a while ago. We did the experiments, and this also will be soon in the archives. These are the results that we get for this result. And with that, I just finish showing you the actual people doing the work in the lab, or most of the work in the lab. This is an old picture, but just to give you a perspective, here's Charlie, he's the guy who actually started the NV Center in my lab. Talita here, about the same time, started the optical tweezer setup. This is a picture taken just a week before the pandemic, just a few days before the pandemic started officially here in Brazil. I think Lucas might be around here. Lucas Kamizaki, you might have seen his poster yesterday. This is a more current picture from this year. with the people in the lab. This was taken for Talita, the defense. She is here. And with that, I thank you for your time and put some reference here in case.
Questions? Oh.
Hi, Sergio. Nice talk. Enjoyed it. I have one question. Like, do phonons created by Stokes scattering in the diamond eventually limit your sensitivity, or is the laser too weak for you to be bothered by that?
Honestly, I never thought about that. I don't know. You mean the anti-Stokes? I think the Stokes. Yeah. The honest answer, Marcelo, is I don't know. I never look into that. Maybe, but you certainly can go around that, cooling it down. Everything I showed you here is for room temperature. But I don't know. We may talk later. There's some things that exploit the phonon degree of freedom that I've been interested in perhaps doing. I remember you talking about some of these things with the Stokes transition. We can talk later.
I apologize because I'm asking the same question to all the NV centers talk, but I still didn't understand the answer actually. So since you mentioned the EPR paradox, do you think you can actually separate spatially the NV centers and try to perform some types of entanglement protocols?
You mean different from what people have done so far?
No, like even okay. So it was done in.
Yes.
I'm just ignorant about.
No. Yes. No. There's actually a well-known result some years back. People from Netherlands, when they do the experiments, Bell-free, loophole-free experiments, and they actually use NV centers for that.
And they use it more for communication, quantum communication.
Yeah, so
stuff,
you can
right?
actually use it if you're operating the single meter regime, of course, a single NV center. Usually you have to go to lower temperatures. I mean, usually you work in cryogenic temperatures for that, because then you want very, very narrow lines.
Okay, because I'm studying how you can use quantum correlations and quantum communication to perform quantum thermodynamics protocols, and I was wondering if can be tested in these systems.
I would broadly say yes, but I would say you that maybe the NV center is not the best defect for that. I mean, particularly, there are other defects like the NV center. It was, as far as I know, the first one that people learn about its details, how it worked, and that inspired to search for new other defects. And today there's a wide variety. So all group 4 actually, even in diamond, produce defects like that. And one that is particularly probably interesting for the kind of thing you're looking at is the thin vacancy defect in diamond. It has a much stronger transition, narrow line width. So the disadvantage is that it only works at cryogenic temperature. So the NV centers for actually technology applications is probably the best, because it has all these features at room temperatures. The other ones actually usually require cryogenic temperatures. The alternatives are these layered materials like the HBN that also people are learning to have this spin coherence at room temperature. There is the silicon carbide that also has interesting defects. So there's now a whole variety of these defects that works on similar principles that one that I described here. I focus on the NV centers because it's the one that I know more about, but there's actually a wide variety. So maybe for your application, the diamond, the NV diamond, certainly at room temperature, is not the best option.
So the idea I had in mind that we are working on is basically to perform a Landauer erasure assisted by entanglement, and we found that it is a measure of steering, which is the EPR correlation. Exactly. So I don't know, maybe we can talk
Interesting.
later.
We did
Okay.
talk later.
More questions? If not, let's think again. Our next speaker is Franklin Rodriguez. So thank you, Franklin.
Then I'll introduce. Okay. Take this out then. Okay, now it's okay. So yeah, so afterwards I'll just nice. Afterwards I'll talk about Bayesian networks, which is the framework that we will use to attack this problem of initial coherences, and how it provides a sort of non-invasive fluctuation theorem, right? And then I'll apply this to initial coherence afterwards. Okay, so motivation and background. We start with the normal setting. We just start with a two-point measurement scheme for a fluctuation theorem. So first, we prepare our system in a thermal state. Yeah, this is harder to point than I thought it would. So we just start with a thermal state that given Hamiltonian, right? Right now, we're just considering unitary evolution in principle. And then we measure our system in the energy basis of this Hamiltonian. Then we allow for a protocol taking the Hamiltonian from time equals 0 to time equals tau, and measure the energy again. And this builds this probability distribution here, where first I have the probability of measuring this eigenstate m, and then the transition probability of going from m to n given my protocol, right? At the same time, we can also define the reverse probability distribution, where I just go to h of tau, let it relax to the thermal bath again, and then we measure again, use the time reverse evolution, and measure in the initial or the final Hamiltonian of the backward process, right? Beta here is just inverse, of course. Okay. With these two probability distributions, we can study the ratio, and then we have what we call the fluctuation theorem. In this case here, the detailed fluctuation theorem, where basically the statement is that the reverse probability distribution is exponentially suppressed by the amount of entropy that I produce along this trajectory, right? This lowercase s here is just the stochastic entropy production, whose average just goes to the normal entropy production that we all know. Work here, since my evolution is unitary, is just the difference between the final energy and the initial energy. And from this fluctuation theorem, we can derive normally that the second law of thermodynamics, where my work is bounded by the difference in free energy that I had. And the gap is filled by this entropy production term here. The problem with this, as we all know, is that when we do the projective measurements, we destroy any coherences that we had in any other basis, right? So these guys here, nice. These guys here, they are not actually the state that I had before. So even though I have quantum effects because of the evolution, I can have interference effects and so on and so forth, I cannot see effects from the quantumness of my initial state, right? And we care about this because there are several instances in which people say that coherences are actually good for work protocols or for engines and any other thermodynamic application that you want to have. However, there are also people that say that it's actually bad, right? I mean, there's this work where by John Gould here and others that you say that the coherences created in the protocol act as friction for the evolution of my system. There's also works here that say that in the linear response regime, I have power losses due to the buildup of coherences. So it would be nice to try to unify this notion of coherence, try to understand when it's good, when it's bad, and yeah, how to do this in a constructed way, right? Okay, so to do this, we use this formalism of Bayesian networks. Basically, the idea of Bayesian networks is that you have some events that you cannot observe, such as diseases, right? This is kind of a gruesome example, but it's the usual one. So I mean, I want to know if a person has cancer or not, and I cannot measure if the person has cancer, right? There's no apparatus that will give me a click if the person has lung cancer, right? What I can see are effects or symptoms that can relate to me having cancer or not, right? The idea is then to apply this to the idea is very similar then to what we actually want to have with these initial coherences, right? Because we can only observe the energy eigenstates. But what we really wanted to observe is the transitions between the eigenstates of my system. So before I projected in the energy basis, right? So yeah, they said, so this is basically the deal. So we just apply the Bayesian networks with these guys being the eigenstates that I had before, and these are just the energy eigenstates that I can observe. This idea was from Kaunan, Gabriel, and Eric. And the probability distribution that I can extract from this is actually quite simple, right? So I have my parent, right? The utmost parent, so the guy that doesn't depend on anything, and I see the probability of having him here. All of these arrows here, they imply conditional probability distributions, the conditional distributions, right? So I have this P of I, and then I have the conditional probability of having energy M, given that I had I before, then the condition of going to J, given that I was at I, and the condition of having energy N, given that I was at state J. One important thing to mention is that all of these guys are positive, right? So there are other proposals for probability distributions that take into account initial coherences or initial correlations, but usually they are complex or they can have negative values, and this one here is completely positive. But it's still not a true probability distribution in the sense that my protocol depends on the initial state that I had before. So this also goes around this no-go theorem that was done for fluctuation theorems, right? Okay. We can also define here then a reverse probability distribution. In this case here, since everything is unitary and my initial state had coherences, it is not so obvious on how to choose what is the initial state of my reverse process, right? When you were dealing with this Bayesian network, since you're putting too much information that you can acquire from your system, it's not so obvious how to build this reverse process, right? There's no thermalization that you can go to say that I lost entropy like this. So in this case, this is just as a picture, since this is unitary, I'm just choosing the initial state of the reverse process to just be the final state of the forward one. And then I can build this protocol here, and I'll have that the stochastic entropy production, which will be 0 here, because the final state, the initial state of the backwards is just the final of the forward, can be described by this term that is the one that we had before in the classical case, plus these terms here, which are the stochastic relative entropy of coherence and the stochastic athermality of my state. So this is just a classical term. I'm just seeing how non-equilibrium my energy distribution is, right? We call this the stochastic relative entropy of coherence and the stochastic athermality, because on average they just go to the quantities that we already know. Yeah. As I said, in this case there is no irreversibility. But let's apply to a non-obvious case, right? To something that is a bit more interesting. Let's suppose that now my evolution is open, right? So I have a reservoir. I don't have my evolution is not unitary anymore, and I have full control over my system. And this is fair to ask, right? If I'm trying to extract energy from coherences, I'm already assuming that I have quite a bit of control over my system. So my initial state will be just an arbitrary state of my system, in general coherent, and the initial state of the environment is just thermal. But the reverse process will be the final state of my system, but the environment is reset into the thermal state. We apply this just to the optical Bloch equations because it's quite easy to do. And yeah, so we have in the unitary case this maximum work theorem that here the variation of free energy will just be 0. So the work that I can extract is tightly related to the variation of coherences and the variation of athermality, right? Extracted work for me is negative here, so negative work is good. No? So we see that if we want to have negative work, we need delta C to be negative. Delta D will be very small here. I chose some parameters where delta D, it's actually very small. This is a classical term, right? So if I want work to be negative, I need to consume the coherences that I had before. If I had no coherences to begin with, then this term will be positive and coherences will be detrimental. And this matches all of the bad cases that I showed before, right? So everything fits in here. The good cases are the same. I always start with a state that has coherences, and in the end, it has less coherences than it had before. So I'm basically consuming the coherences to produce work or to extract work. Okay, so we just see here the case in which this is unitary. Then what you actually want to have is an evolution that is not adiabatic, right? If my evolution is adiabatic, then the variation of coherence here will be just 0. The coherences will be locked. They will be just a phase will change, but the relative entropy of coherence is agnostic to phase, so it doesn't matter. So yeah, so if we want to extract work from coherences, we also need to go beyond the adiabatic regime, which also fits that bad case in which we were in linear response, right? So if we're very close to being adiabatic, this is usually not good. Okay, this is just some plots showing what's happening. So if I have no coherences in my initial state, then of course my work output will be positive because delta C is positive, and we can see that delta C plus D fits perfectly on the curve, so there's no entropy production because the system here is unitary. I'm just taking the unitary case. Whereas if we have a 0.3 here, this goes from 0 to 1, it's normalized. So I have a little bit of coherences. I can already have some work extraction regime. Okay. Something nice also about this probability distribution is that I can go beyond average values, right? So I can plot some linear response here. This is okay because this is just for the thermal case. But we can also generalize linear response in the case of initial coherences. But I didn't put anything here because the formulas are quite gross. I didn't manage to put it in a nice form, so we're still trying to deal with this. Okay, let's go to the open case then. If it's open, then in general, this guy will be bigger than this, right? I'll have entropy production involved. Right? So it does not suffice for delta C to be negative. It does not suffice. I have to be faster than my environment. So there will be a competition between delta C going to work and delta C going to the entropy production, going to the correlations between system and environment, or just taking the environment out of equilibrium. So we see this quite nicely here, that if this tau W here is just the work extraction time scale, it's just the Rabi time scale. If the coherence has a much longer time scale than the work extraction time scale, then I have a huge window to extract work from my system here. And the biggest amount of work that I can extract, it's exactly at the Rabi frequency that one would expect. But as I increase the dissipation, then the time scale for dissipation also decreases, becomes comparable with the work extraction time scale, and then I can extract less work, and I need to do this quicker. Right? So there's this trade-off that you have to think about. Okay. I still have some time, so yeah, I mean so for this, to have the work extraction, I must be in the non-adiabatic regime, and I must extract work before the coherence, which fits with all of these 4 examples that I gave in the beginning. But one could argue here that, okay, you extract coherences, and then you don't have any coherences anymore. After this, I mean, then you're doomed, right? I mean, you always, the coherences will build up again, and this will just be bad for work extraction again, right? So what we thought is to try to apply it to a case in which you have coherences being injected into the system, that coherences can be injected inside of the system at every point in time, right? So it's not that I start with initial coherences, but rather my environment gives coherences to my system. This can be achieved in this generalized Gibbs ensemble case, where I have some conserved charges, just like in the normal Gibbs ensemble, but these charges don't commute amongst themselves. This can be applied for magnetizations in the Heisenberg interaction, where each magnetization in every direction commutes with the Hamiltonian, and for energy and squeezing for the beam splitter interaction, where Gabriel, who's also here, studied this in the context of linear response as well, right? Okay, so the way that it works for you to get the fluctuation theorem is the same as we had before. But what I like a lot about this one is that this is more in the spirit of the normal fluctuation theorems that you had, because everything is equilibrium somehow, right? So the initial state of my reverse process is also in equilibrium, just with respect to the change of the charges that I had before. And thus, the bound that I have here is also everything in equilibrium. Before, the delta C was dynamical, right? But here, it's just a difference between the coherence that I had, that I will have in the final GGE with respect to the base of the initial GGE, right? Okay. And the gap, as before, is just the entropy production. This is still ongoing work. This is not some the previous work we already published in communications, in communication physics, but this one is still ongoing work. I'm just giving a snapshot here because I think it's interesting. Just to begin with something simple, we just apply this in the case of transport. So all of these all of these equilibrium quantities here that I vary will all be 0, because the initial charges are the same of the final charges. This is just transport, right? There's no time dependence. So I just have this variation of these affinities, right? Yeah, I forgot to say these are just the affinities that I have in the Gibbs case. So if this was connected to the Hamiltonian, then it would be just the inverse temperature with the number operator. This would be just the inverse temperature times the chemical potential, so on and so forth. So this is just a generalization for any charge that I put there. And then I have just the normal, this just becomes the normal entropy production for the case in which they commute. It doesn't change its form, it's the same. And just doing a very simple example here, just the Heisenberg interaction, I put the environments here, but my environments are just 1 qubit, I have to admit. This is just to begin, just to check. But if I prepare this state here as thermalized with a magnetic field that is in the z direction, and I thermalize this one with a magnetic field that is a little bit tilted in the direction of the x direction, and calculate the magnetization currents that I have here, we already see that this non-commutativity gives us some huge advantages, right? So I'm comparing this with the case that where is it? I'm comparing this with the case where here I would have just magnetization in the z direction, but the temperature would be a bit different. So I would have transport, I would have entropy production. And I just make the parameter regime where this entropy production is the same as the one that I would do by rotating my magnetic field instead of changing its strength, right? So the classical case, quotes, is this dashed line here, which is this delta. There's only a single current because it's just the current in the z direction. And the one of this GGE is I will have currents in the x direction, the z direction, and the y direction. And we can see that there is a huge current that starts linearly in time instead of quadratically, that is perpendicular to the plane of both magnetic fields, right? So there's this, which has a different parity of the other two currents here. So we are still not very sure of this. We have to check, but it feels like this violates the TUR. But in the derivation of Chimpanaro that he presented before, when you build the fluctuation theorem, it is necessary for you that when you do the probability, should be P of Q over P of minus Q, right? And since the parity here is different, this doesn't work for the TUR. So we're still investigating this, but I thought it would be something cool to show to you guys. This will be soon in archive. Well, that's all I wanted to say. So we created this Bayesian networks to account for coherences and correlations. I didn't show here, but we also apply this to correlations while maintaining positive probabilities. It's not a true probability distribution, but it's still positive probabilities, right? So something nice. And also that initial coherences, they can suppress dissipation or boost currents, as we just saw here before. That's it. Thank you very much.
Thank you. Questions?
Hi, Franklin.
Hello.
Thanks for the talk. I have one question. Usually we say that there's no free lunch. In the first example that you gave, the cost is easy to spot. It's just you have to build up coherence in the initial state.
Yes.
In the second example, where is the cost? Is in the buildup of the reservoir? So
This is a good question. The honest answer is that I don't know exactly. I mean, for instance, I don't know what would be the cost of just having a laser that has squeezing in it, right? And then I'm just trying to thermalize, quotes, a mode to a laser that has squeezing. What would be the cost of this? I don't know very well. I mean, I'm just, from my standpoint, I'm just assuming that I have these reservoirs for free. But what's the cost of having this reservoir? I mean, it's a fair question, but I wouldn't be able to answer.
Thanks for the talk. I was not aware of this Bayesian, I don't know, network
I also
to
don't.
generalize the two-point measurement scheme. I was aware of another framework that is by Juan Pablo Paz, where basically they use an ancilla and perform a POVM. And also this allows to preserve coherences. And I wonder, I don't know if you know about this, and I wonder if how this relates. And I don't know, because at this point we have a zoo of ways of characterizing the probability distribution of work.
Yeah, I'm aware, but I think that this probability distribution from Juan Pablo can be negative, if I recall correctly, right? And I don't know. I mean, this is true. I mean, there is a zoo, but the way that I see this is kind of I don't know, we have the Wigner distribution, we have the Hosimi distribution, and each one can be used in a different way, and they have their own caveats, right? So I would take like Juan Pablo's to be something Wigner-like, and mine to be something Hosimi-like.
So it's more like, so they are all equivalent. They don't give different
I
results.
I don't know, I
yeah,
don't
that
know.
would
But
be
this is
my
a very
question.
this is a very good
That would be
question.
my question.
Yeah, I don't
do
know.
we have the same result? Do we get the same moment of the work distributions or something like this? Or
I mean, it is the same in that if you don't have initial coherences, they will go to the
work
average that you
point,
want,
yeah.
and also to the TPM average. So in the sense, it is the same.
Could be interesting to study what happens with coherence.
No, for
because-
sure, for sure, for sure. I'm keen to that. I'm keen to that. We can talk later.
So first a comment to Federico's question. The POVM is the same as the two-point measurement. It's only the way that you do the experiment. You imprint this on an ancilla, etc. But at the end, if you measure,
Yeah, it's a one-point measurement scheme from Juan Pablo. Eh?
in a sense, you do, because you are writing the coherences in the correlations with the ancilla. So these are in the entanglement. So if you are able to perform collective measurements on the ancilla and the system, then you're right that you're not destroying. But if you trace out and you look at one, the system or the ancilla, you destroy. You imprinted. Okay, okay, okay. Yeah, yeah. Yeah. Thank you. And then I had the question for you, sorry.
Yeah, yeah.
And the question was actually related to this. So I maybe missed, how do you measure these Bayesian networks probabilities?
Yeah, I mean, here we cheat a bit in that we suppose that we can measure the eigenstates of our system, right? So we first it's really like this. I mean, just a second. So yeah, all of these guys here, they're all measured. So we measure the eigenstate of my system, and then I measure the energy after that. Then I throw this away. Then I do this several times, and then I put in my pocket all of these conditional probabilities that I had. So
all
it
these-
is
all
not
these
single
arrows.
shot. It's
So
two
first
shot.
you measure these vertical arrows.
Yes,
no?
exactly. So it's not a single shot experiment, right? I mean, it's never a single shot. You always do averages over several stuff, but here it's two shot in the sense that you actually do two different experiments, right?
Okay, thanks.
Yeah, no problem.
More questions? Okay, if not, so let's thanks again. And you have the cough break right now. the last session of the day and the conference. So now we have John Good. Thank you, John.
Thanks a lot. So let me join in the other speakers and just to say thank you very much for inviting us, and we had a wonderful week. It's actually nearly 10 years since I was in CBPF, and it's nice on a workshop on more or less the same topics, and it's nice to see all of the new things and see some familiar faces. Anyway, so I'm going to talk today about two things, I would say, which are interconnected. The first is this sort of quantum Mpemba effect, and the second is something which was inspired by the work on Mpemba effect, which is the stuff we're doing in information geometry. So the first part of the talk actually is going to be about this paper, which was published actually, I guess, a couple of months ago. You probably know Mattia is here in the audience. So Mattia was a visiting PhD student in Dublin, but he just recently graduated and now joins the group for a postdoc. I'm just trying to work this thing. How does this work? I know it doesn't matter. Anyway, Oisin is the first button. Okay. So Oisin is a PhD student that just handed in his thesis in Dublin. He's looking for a position. He's an excellent student. Anybody knows anybody who's looking for a very good postdoc, contact Oisin. Christia, who gave a beautiful talk yesterday, you all know, she was in Dublin, obviously, for a while and moved back to her native country. And obviously, I was just coaching the other three guys, deserve all the credit. So let's get started. So the Mpemba effect, probably you've all heard of. If you Google it, you're going to find kind of these fantastic looking photographs of kind of crazy Russian people or people in cold countries launching pots of boiling water over their head in freezing temperatures and making these beautiful images. An Mpemba effect is the observation that sometimes, hot water can freeze faster than colder water, okay? And this was an observation that was actually around since the time of Aristotle. About 2,000 years ago, Aristotle has in his writings, there was a bunch of villagers in a mountainous place in Greece, and they were essentially immersing reeds into hot water to freeze these reeds quicker to make fishing rods. I don't know why you would do that, but they were doing that. And you see then other people like Descartes, etc., had made this observation in the last 2,000 years. The effect gets its name from this guy, who's Erasto Mpemba, and this is the kind of folklore. In the 60s, he was a student, high school student in Tanzania. They were in a home economics class. They were making ice cream, okay? You make ice cream, you have to heat a sugar and milk solution up, boil it, and then you leave it cool down, and you put it to the freezer. But he was in a rush, so he put it into the freezer without waiting to cool down. And he noticed that his sample froze faster than the rest of the samples that waited for it to cool, right? And so he said this to the teacher. The teacher said, this is nonsense. It violates Newton's law of cooling. And he kind of was persistent. And a physicist called Dennis Osborne visited the high school maybe a year later, and Mpemba told him about this, and he said, okay, I don't believe you, but I'll do some measurements. And they did this measurement. You can't really see it properly, but you have the initial temperature of the sample on the x-axis, and you have the time to freezing on the y-axis. It's a pretty rudimentary measurement, but nevertheless, there's some sort of evidence that this was a real thing. And they wrote a paper about it. And Mpemba went on to become a gameskeeper in Tanzania. So he didn't do physics anymore, but this is the paper. It's actually called Cool, okay? So it's probably the best title ever, right? So in physics education, 1969, and it's like hugely cited now, right? So this is him outside the Royal Society of Chemistry. There was a prize given out by Royal Society of Chemistry for people who could actually make some sort of headway into the phenomenon, okay? So 2,000 years, and now there's a flurry of work in the classical sort of statistical mechanics community about Mpemba effect. Why? 2,000 years it's been around, and I'm going to come to that. So you see here there's various different systems, granular fluids, Maxwell gases, spin glasses, all sorts of things. So a huge amount of activity coming from classical statistical mechanics. And the reason why there's such a large activity now is because in 2017 there was some theoretical breakthrough in the field of classical stochastic thermodynamics. It's super simple, okay? So this is a paper that was in PNAS in 2017 by the Raz group in Weizmann in Israel. And they were looking at what would be seen as a sort of staple of stochastic thermodynamics, right? You just have a classical rate equation, a Pauli master equation, okay? which describes essentially the evolution, Markovian evolution of initial probability distributions on some energy landscape. You have an example here on the right-hand side of a kind of tree-level system where you have energies, barriers, et cetera, which define transition rates. And then you propagate your vector by means of this simple equation. The master equation is detailed balance. So any initial probability vector goes towards the same thermal state as the fixed point. It's set up like that, okay? If you look here on the right-hand side, just to give you an idea, I mean, you could really give this to an undergraduate and they would do okay with numerics. Basically, you have the probability vector space is like a simplex, right? So for a tree-level system, what you see here with the curve red to blue is the so-called quasi-static locus. So that's basically the set of probability distributions in your problem which are Boltzmann distributed. But of course, in reality, when you're far from equilibrium, you take some initial state and it can go anywhere in that simplex, okay? It doesn't have to follow the quasi-static line. So what's the big deal, okay? So well, if you look in the paper, they sort of make some definitions, right? So the first thing they say, let's try to define a Mpemba effect, okay? So the first thing is you need some distance or distinguishability measure on the space of probability distributions, okay? So you have something like this. It could be a divergence, like a Kullback-Leibniz divergence, or it could be like some sort of norm. Doesn't matter, okay? And then you need three temperatures, a hot temperature for your initial vector, a cold temperature for the colder vector, and you have your fixed point, TB, okay? And you basically know that in that set of equations that you choose some probability vectors which are Boltzmann distributed at different temperatures, a hot and a cold, okay? They'll relax to the same equilibrium state. And you say that, well, look, a Mpemba effect exists if there's some time Tm such that the distance between the hot trajectory on its way towards the fixed point is less than the distance between the cold trajectory and the fixed point for all t greater than Tm, okay? So the curves will cross, the distance curves cross, which means, you know, the hot trajectory is reaching the fixed point faster, okay? This is the kind of mathematical definition. And because this is such a simple equation, you can kind of expand out the solutions of that rate equation very simply. So the probability as a function of time for an initial vector can always be expanded in the set of the eigenmodes of the Liouvillean, okay? So this is what I show here. You have the thermal fixed point, and then you have a bunch of decay modes, okay, where the time scales of the decay modes are dictated by the eigenvalues. So these V2s are the right eigenvectors of the Liouvillean, and the A2 up to AN are the overlaps between the initial state and the fixed point, okay? So you know that if you take such a thing and you basically take the long time limit, you see that asymptotically the time scale for relaxation is dictated by the inverse of the spectral gap. So the sort of largest non-zero eigenvalue of your rate matrix, right? This is kind of statistical mechanics, basic statistical mechanics. And they just realized this. Well, look, you know, you can find situations where, for example, the overlap between the initial cold state and the fixed point, okay, is greater than the overlap of the hot initial state and the fixed point, okay? And you have this sort of non-monotonic behavior as a function of temperature. Furthermore, they realized subsequently that you can even get situations where your initial hot state completely cancels the overlap with the slowest decaying mode, and therefore your relaxation timescale is exponentially enhanced, right? So you've exponentially faster cooling in that case. So this is a kind of very rudimentary explanation, and lots of people got interested. So it's simple, but after 2,000 years, somehow, at least it explains the effect in a wide class of systems which are of relevance to stochastic thermodynamics, which is the Markovian master equation. This was turned into an experiment in around 2020 by Bichauer, and this is the type of typical setting for stochastic thermodynamics, classical. You take some colloidal particle, which is modeled by a sort of microsphere in a sort of tunable optical tweezers potential. So they can generate kind of arbitrary trapping potentials and then study very accurately the kind of trajectories or positions of the colloidal particle as a function of time. So they have a lot of control. This would be very typical of the settings that would have seen the first experimental demonstrations of fluctuation theorems for classical stochastic thermodynamics, for example. And indeed, they were able to set up this problem to modify the optical tweezers potential in such a way that they were able to plot this type of distance curves. Don't ask me how they manipulated that exactly, because I forget. And you see that these situations where your hotter initial state will relax faster than the colder initial state. So it's a kind of experimental proof. And there's a subsequent follow-up where they do this inverse Mpemba effect. And a lot of people got interested. OK, so quantum systems. So what's happening, right? So this is actually a cover of PRL in July. And you see 3 papers that were highlighted on the same day, where I'm going to comment on this later, but there's a bunch of different scenarios whereby you can get Mpemba physics in the quantum dynamics, right? So you have dissipative systems, okay? This is an experiment in an ion trap in Israel, okay, where they observe such physics, which I'm going to talk about soon. And then you also see in the top is another experiment in a trapped ion analog simulator in Rainer Blatt's group, where they basically look at a slightly different scenario, which I'm going to talk about a little bit later, which is they call Mpemba effect when you sort of break a symmetry of a problem that has a symmetry, and you look at symmetry restoration faster for certain states which have more symmetry breaking. But I'll come to that. So let's start with the dissipative systems, and now let's start to think about the Liu and Raz work, okay, in a quantum way, okay? So what's the difference between a classical Markovian problem and a quantum one? Well, of course, we propagate density matrices, and let's stick with the Markovian paradigm. So we're going to just use the standard workhorse of the Lindblad master equation. And one thing I suppose that we all know, this community would know very well, is that your spectrum in general can be complex, right? The eigenvalues of your Liouvillean come in complex conjugate pairs in general, okay? So you have the von Neumann part, you have the dissipative part, and you can see that basically the Liouvillean is a superoperator. Okay, so its eigenspectrum now is operators itself, right? So the right eigenmatrices are the eigenmatrices of the Liouvillean, and the left eigenmatrices are the eigenmatrices of the adjoint, okay? Which describes the propagation of operators in Lindblad, okay? So you always have one, you assume one non-degenerate lambda equal to 0 state, which describes the fixed point, and this is the kind of structure that we're dealing with. You can do exactly the same expansion. You can write down the general solution of the Lindblad master equation if you can diagonalize the Liouvillean in terms of its decay modes and the corresponding overlaps, right? So here you see that the time evolution is dictated from any initial state towards your fixed point tau by a bunch of decay modes, which are sort of written like this, where RK are the right eigen matrices of the Liouvillean, and this sort of inner product here is equivalent of the overlaps that they studied in the original classical Mpemba paper, okay? And you see that the spectral gap again, okay, defines asymptotically the relaxation timescale of the problem. So the timescale it takes in the long time limit for you to sort of go towards a steady state. Okay, so we started actually, this is a story, and Christian Mattia can tell you, we just did a journal club in the group last summer, and we were looking at this paper with Federico Carollo, Lesanta, Levinovsky, who asked a very interesting question, okay? They say, okay, given this structure of a Lindbladian general, they don't assume any detailed balance, okay, can we find an initial state which is transformed unitarily such that I can kill off essentially the overlap with the slowest decaying mode? Can such a unitary be found? I take some state, do a unitary, and then I have exponential speed up towards my fixed point. Indeed, they show analytically that this can occur. You can always find such a unitary on your initial state under some restrictive conditions. I'll talk about the restrictive conditions now. What are they? Okay. The first ones are they restrict themselves to pure states at initial time 0, okay, which is restrictive. Okay. Of course, it becomes mixed as a function of time because you have a dissipative system. Okay, but other than that, there's also one other key point that's required in their proof, which is that the spectral gap, okay, the inverse of which describes the timescale, is defined by a strictly real eigenvalue, which is, of course, restrictive because there's no real need for that to occur. In general, the spectral gap can be defined as the real part of a complex conjugate pair, okay? Because if you have a complex conjugate pair, your asymptotic state that's evolving in time looks like this. So you have these two overlaps to think about eliminating, and it doesn't look likely you can construct a unitary due to the non-Hermitianness of L2, but this is another story. So we started from this, and we were thinking, well, how can we kind of generalize this a little bit? The other thing that's cool about what they did is that they don't assume that it has to be a thermal fixed point. You're really exponentially speeding up towards any fixed point, okay? Okay, so we wanted to kind of be a little bit more restrictive and strict. So we were going to focus on specifically the master equation of Davy's form, okay? Most people here in thermodynamics will know, which has a thermal fixed point, okay? So this is basically the domain of Markovian quantum systems with detailed balance. So what does detailed balance mean mathematically at the level of the master equation? This was a big topic in the 70s with Robert Elischke, who's still going strong. Basically, in a Davy's generator, the mathematical structure is such that the dissipative part of the generator is Hermitian under this funny inner product, which is called the KMS inner product, which becomes the standard Hilbert-Schmidt norm in the limit of infinite temperature. Okay, and given this sort of mathematical condition, some nice things happen. For example, the dissipative part and the von Neumann part commute, and you can see that they share a common eigenspace, which are simply the outer products of the energy eigenbases of the Hamiltonian onto themselves, right? With eigenvalues, which are the energy differences. It's kind of structure of the Davy's master equation. And it's this structure for what is important for what I want to say, which is the following. If you have such a scenario and, okay, you don't have any degeneracies in your Hamiltonian, then we all know, under these conditions, that the part of the master equation describing the evolution of populations and the part of the master equation describing the decay of coherences, they have a subblock structure. Okay, so if you write the superoperator as a matrix, you see something like this. So you really look at the part which describes decay of population, which is kind of like the classical master equation that we originally looked at. And then you have this bigger part, which is essentially describes decay of coherences. And the other thing, which is kind of essential for what I want to say, is that this structure is such that left eigenmatrices, which correspond to populations, are diagonal in the energy eigenbasis with purely real eigenvalues. And left eigenmatrices, which correspond to coherences, are purely off-diagonal in the energy eigenbasis, okay? And it's these left eigenmatrices which enter into the mode overlaps, right? So this is the key. And you see something which is almost trivial, okay? Which is that these left eigenmatrices, which are pure off-diagonal in the energy eigenbasis, can always be eliminated by any transformation that brings your initial state to be diagonal in the energy eigenbasis, okay? We'll make those modes go to 0. So you have something like this. You start and you've deleted the sort of ones which have this complex conjugate pair, okay? So now, if you have such a scenario, if you have such a spectrum, your new timescale is going to be defined by this new spectral gap, which in this case is going to be like, you know, the third or fourth eigenvalue. So actually, you don't even need a unitary. Any transformation will do. And you might ask yourself, come on, is this a Mpemba effect? You've not mentioned temperature, cooling, or anything. You just told me a prescription to get an exponential speed up, and that's true. You need some notion of order on the initial states, okay? So in the case of the classical work, it was some temperatures of the initial states, which, by the way, have nothing to do with the temperature of the master equation because they're not in equilibrium, right, with the fixed point. So what we introduced is something which is very common in quantum thermodynamics, which is to sort of use the notion of non-equilibrium free energy. And the nice thing about non-equilibrium free energy is that it can be related to a relative entropy, okay? So the first time I've seen this done is this paper by Matt Donald in the 80s. So the idea is you just relax the assumption of applying the free energy to thermal equilibrium states, and you say, I can do it for, you know, an arbitrary density matrix, and I assume that the temperature is that of the fixed point. And if you do that, you see something natural, which is you see that you get an object which looks like this, where basically you have the equilibrium part, and if you have an out of equilibrium situation, and you have this additional contribution from the so-called relative entropy, right? And that's nice because, as you know, the relative entropy is positive. It's not a distance in itself, okay, but it's upper bounding distances in general. But key point for Mpemba physics is that it has data processing inequality. It's contractive under completely positive and trace-preserving evolution, which means that you'll have sort of a monotonic decay of the non-equilibrium free energy towards the thermal fixed point, right? So, some other words about it. Of course, if you're more happy to work with entropy production, okay, if you take the derivative, okay, of the non-equilibrium free energy, you can recover the famous result by Herbert Spahn and Joel Lebowitz for semigroups, which is the positivity of the entropy production rate. You see that basically it's just a derivative with respect to time of the non-equilibrium free energy. Okay, this is in this very nice review. You'll see very well done in Gabriel and Mauro's review. The other thing that I can say about the non-equilibrium free energy is that there's a nice division if you want to study processes which involve coherences in populations. okay, so that you can split it up into two further relative entropies, one of which is a Kullback-Leibniz divergence between the time-evolving probability vector and a fixed point, okay? And the other one, which is actually, strictly speaking, the relative entropy of coherence, which is a quantifier of coherence given some basis, in this case, the energy eigenbasis. Okay, so let us define a quantum Mpemba effect now, using the non-equilibrium free energy to quantify order. So we have three states. We have an initial state, which is arbitrary, okay? It can be whatever you want. You choose it at random. You have a rotated state, okay, which is going to be this one that you rotate into the energy eigenbasis. Actually, it could be a completely positive and trace-preserving map. It doesn't have to be unitary, but for the purpose of this, we'll say it's unitary. And you have your fixed point, which is thermal. And you want the order so that your rotated state has a higher non-equilibrium free energy than your non-rotated state. So non-equilibrium free energy is kind of playing the same role for us as temperature did in that classical paper. And you say a Mpemba effect exists if there exists some time scale such that the curves cross, so that the rotated state is less than the non-rotated state for all times greater than this time scale. And the key finding of our work is that if the generator, okay, has a spectral gap defined by a complex eigenpair, then a transformation, unitary otherwise, can always be found such that an exponential speedup in a genuine Mpemba effect occurs. I will give you one. Diagonalize your initial density matrix and make it, push it into the energy eigenbasis and do population inversion. This will have a higher non-equilibrium free energy understate. It's a unitary transformation. It's very easy, okay? So if you take a qubit example, okay, so these plots were made by Mattia, Christian, and Oshin. You see up here on the block sphere that the green point represents the initial state. You can see it's got coherences, okay? The purple state represents the rotated one. And you see that essentially the one with coherences has a longer distance to travel towards the thermal fixed point than the one that's diagonal in the energy eigenbasis, okay? So you see here in the first plot, basically the purple guy, okay, and the green guy, which starts off with a smaller free energy, crosses the purple guy. And this is the Mpemba effect. In the inset, we're just showing that basically it's an exponential speedup, an exponential cooling, okay? Okay, so that's the first thing. And is this just a consequence of being simple qubit system? And actually, if you go to a more non-trivial example, take a number of different spins. Here we're looking at transverse easing for a small number of spins, which has a much more complicated spectrum, but still you have this desired property of the spectral gap being defined by the real part of the complex conjugate pair. You see the same, okay, at a longer time scale. And that time scale will diverge with system size, okay? Right, so that's basically what we did in the paper. And what I want to tell you now, I have no idea what time I'm on, by the way. Sorry? 25 minutes, good, perfect, so I have plenty of time. It's 40 minutes, right? Yeah, good. So, okay, so this is kind of the results of that paper. And as I said, it's a really simple effect, but lots of people studying it, lots of experiments, etc. It's simple, but also, in my opinion, is profound, right? Because it gets thinking a little bit about really the essence of non-equilibrium statistical mechanics, which is you can find things very far away from equilibrium in linear response, which are highly counterintuitive. This Mpemba effect being an example, right? You wouldn't expect this to occur if you didn't know about the Mpemba effect. So this, I want to tell you now a little bit about information geometry and give you another kind of spin on Mpemba effects. I'm on sabbatical this year, and I said I'll take a topic for my sabbatical to learn a little bit about, so I started to learn about information geometry. I'll give you the basics of it, right? And my student, Letizia, got very interested as well, and within about 3 weeks, she knew infinitely more than me, so she started to teach me about information geometry very quickly. We put this paper in the archive relatively recently, and I'll give you a little bit of the essence. I'm not going to talk about it all because it's a bit technical or whatever, but there's a huge amount of interest in the last 5 years in statistical mechanics, classical statistical mechanics community, on the interplay between geometry and dynamics, right? There's always been good links between geometry and thermodynamics going way back like 50 years, but quite recently people are really thinking about the geometry of stochastic processes, okay? So there's these nice works by Ito, which basically kind of map, really study in detail the geometry that's induced, okay, by classical Markov master equations with detailed balance and tried to link various geometrical properties towards entropy production, entropy acceleration, etc. The other thing, which is connected to some of the other talks in the paper, is that what you get from thinking geometrically about stochastic processes is actually geometric speed limits. Diogo, Gerardo have a nice work on that. But fundamentally, you see in this paper, which is a classical paper by Jason Green's group, also with Adolfo Del Campo, they look at sort of the emergence of various different uncertainty relations, which are a consequence of the mathematical structure, okay? So we were kind of inspired by these, and we wanted to see what can be done at the level of quantum stochastic thermodynamics. So the idea of information geometry for classical stochastic processes is very simple. Information geometry is the mathematical study of probability distributions that are parameterized, okay? So you can have multi-parameters in your probability distribution, and now you vary the parameters, and you think about the manifold of probability distributions that emerge from varying those parameters, and you start to ask questions about what is the underlying geometrical structure that you get. This is what the mathematicians do. If you apply it to kind of stochastic processes, you think that in your process there might be some parameter which depends on time. It could be a Hamiltonian parameter or whatever, a rate, whatever. And you see that you get some structure. Every single point on this manifold is a probability density at some value of the parameter. And you can ask questions like, given I understand the geometry of the state space, what's the shortest path, okay, between them in the state space, statistical length, okay? So we typically learn about Fisher information in the context of metrology, but Fisher information is natural when we think about this information geometry. Another way of thinking about what Fisher information is, if I take a probability vector with some parameter theta attached to it, and another probability vector with in parameter space, say theta plus delta theta, so a small variation, the Fisher information tells you how distinguishable these two probability densities are. So on the manifold, the metric that actually exists of probability vectors, which are parameterized by theta, okay, are described by the so-called Fisher information metrics, which look like this. You see the derivatives of the log of the probabilities weighted by this sort of probability. And there's another important result, which I'm sure Diogo and Gerardo know very well, because I learned it from their paper, which is in the classical mathematical community, there's an extremely important result called Chesnov's theorem, which is very beautiful. It says that in the space of classical probability distributions, which are parameterized by a vector of thetas, okay, the Fisher information is the uniquely contractive Riemannian metric on that space. Unique, okay? So it's a very strong result. So what these papers do is take a slightly different viewpoint, which for me is very interesting, okay? Which is rather than think about the theta itself as the parameter, think about time as your parameter. Why not? Time, temperature, etc. Okay? And you see that if you look at this, then basically your line element squared, okay, is up to some constant prefactor the Fisher information with respect to time. Okay? So ds squared, f of t dt squared, I say, okay, ds dt, the velocity in your probability space is the square root of the Fisher information with respect to time. So it measures how fast your probability vector is evolving. It's the instantaneous velocity of a probability vector in space, okay, sorry, in time. And then what you can do is you can integrate this to get a statistical length. Okay, you integrate the velocity over time. So this is the so-called statistical length. That statistical length, for example, can be any one of these sort of dashed curves, depending on your process. And then if you're lucky, you can work out what the geodesic is, okay? The shortest possible length. Okay, so how about quantum mechanical generalization, where you deal with density matrices as opposed to probability vectors? You can always do this, and there's only one key difference. And the key difference is that rho of theta and d rho d theta, okay, do no longer commute in quantum mechanics, so you can have coherences. So if you do a sort of general expansion of an arbitrary dynamics, so yeah, I mean, you can always do what I've done here. You can write the evolution of a density matrix in this way with some sort of Hermitian operator h of t, which is constructed like this. Don't want to get into the details. You see that if a Fisher information can be defined with respect to time on the density matrices, okay, where you get a diagonal component, which is just a classical Fisher information on the probability. Okay, this is in the instantaneous basis on the probabilities of the state. And then you get this off-diagonal term. And this off-diagonal term is very interesting because notice there's an F function here. And this is due to the results of Dennis Petz, who's a very famous sort of quantum information theory mathematical physicist, who showed in the 90s that actually there's no unique contractive Riemannian metric on the space of probability densities. There's actually a family, okay? So it turns out that you can get a whole family of Fisher informations thinking like this in the geometrical way, one of which, the SLD, okay, is the one that's used in metrology, the symmetric logarithmic derivative, but there's a bunch of other ones, okay? It turns out, which is quite interesting, that mathematicians know that the geodesics are only analytically computable for two of these possible members of the family, the SLD and the so-called Vigneri-Anasi skew information, which I'll talk about, right? There's also this Kubo-Mori-Bogologov one, which is also very important in statistical mechanics, but I don't want to talk about it. You have a bunch of them. Why is the SLD used in metrology more? Because the SLD is the smallest Fisher information. The rest of them bounded from above, and therefore, in terms of Kramer-Rao, it gives tightest bound for estimation of a parameter, okay? But here we don't care about estimation. We're really using the Fisher information as a tool to get an insight into this sort of abstract probability space to try to understand problems in statistical mechanics, okay? So here are the geodesics. I'm not going to really use them much. And here is now when I apply this formalism to the Mpemba effect that I just discussed, the paper with Mattia, Christia, with Oshin. So on the left-hand side, you see the statistical distance, so the integral of the square root of the Fisher information with respect to time. I think this is for the SLD form, okay? And what you see is that the length for the non-rotated state, namely for the slower dynamics, is longer, okay? And for the red one is shorter. However, we do not exploit a geodesic in that protocol. The geodesic for the state with coherences, which is slower, is actually shorter than the one that's rotated, which is interesting, okay? And the other thing you can define is something like a degree of completion. That's when you take the statistical length as a function of time and you divide by the total length, so you get a number between 0 and 1. It quantifies how much of your process is actually completed at time t. And that's actually the same tool that they've used to analyze this experiment, which appeared earlier this year in classical physics, which is to show that heating and cooling are fundamentally asymmetric, meaning that in certain circumstances, heating is always more difficult to do than cooling, right? And they make a geometrical argument based on exactly the same argument for classical physics there. So that's the first statement I'll make geometrically about the Mpemba effect, and I'll just make the last before I follow up. So there's lots more in that paper with Letizia about geometry and statistical processes, but I was kind of happy with it as a first go. So something that I've never done before is I want to present some results that we did this week when I was at the workshop with Mattia. Okay, so now, what's annoying at the moment about this Mpemba story? There is a proliferation of different Mpemba effects. Closed systems, classical systems, dissipative systems, whatever. And you see this question mark that was done in the popular article that was in PRL. I would argue that all of these are same, and they're all manifestations of restoration of symmetry, okay? Continuous symmetry. So in all these examples in Mpemba, whether it's thermalization or in this case of the closed system, which I'll explain in a second, okay, you break some continuous symmetry. In the case of thermalization, you break time translational symmetry and it's restored in time. So you need to find ways which is universally applicable to quantify the degree of asymmetry breaking in time, okay? So what is done in the closed system case is quite interesting because Pasquale Calabresi's group in CISA has been very active in this. You say I have some spin chain or some circuit which has a continuous symmetry. Let's say it has U1 symmetry. So what does this mean? It means that it preserves total magnetization. But I can always start, in a state which breaks that symmetry. I can work with some sort of tilted antiferromagnetic state which will break that U1 symmetry, meaning it will couple symmetry subsectors. And you can find, believe it or not, situations in these type of things where you break a continuous symmetry where the symmetry is restored faster from states which have further symmetry breaking at time 0. This is for U1 symmetry. You can do the same for SU2 symmetry. And in the case of thermalization, it is time translational symmetry that you're breaking. So what am I going to say here? So if you look at the origin of Fisher information's different sort of structure. So we had the SLD, we had the Kubo-Mori-Bogologov, and then we had something called the Vigneri-Anasi skew information, which was actually invented by Wigner, not knowing it was a Fisher information at all. what Wigner was doing, yeah, if you read the paper, is actually very nice. He's asking about the consequences for measurements if your system has a global symmetry. Okay, this is the idea. Okay, they have a significant influence on measurements, and you can write the Wigner-Yanasi skew information in its off-diagonal part. It looks like this. It's interesting also because it's the only Fisher information which doesn't require diagonalization of the instantaneous density matrix. Okay, and this turns out in modern language. We saw a very nice talk yesterday by Gerardo, who's asleep now, about resource theories. And in modern language, it's formally an asymmetry monotone. Okay, so what it can be shown by this very nice work by Iman Marvian, who I recently visited in Duke in the US. He's very interested. His topic is essentially symmetry. Okay, in quantum information, he basically he proves that the Wigner-Yanasi skew information and the other Fisher informations with respect to time are formally measures of the amount of symmetry, asymmetry in your state. Okay, and now you have a beautiful unified way of thinking about all possible Mpemba effects. So, for instance, if you think about Pasquale Calabresi's work, this is the kind of scenario they use this entanglement asymmetry, but it's, in my opinion, has nothing to do with entanglement, just fortuitous. Okay, if you have, so we were working a lot with U1 symmetric random circuits. Don't worry what they are. They're just brickwork circuits where each of the 2 qubit gates are chosen to respect sort of like a structure like this. So you have some initial state, okay, which breaks the symmetry, and then you engineer 2 qubit gates which are otherwise random, which preserve excitation number. Okay, you can always do this. And if you apply the Wigner-Yanasi skew information in this type of context, you see it beautifully shows up this Mpemba physics, right? Because it's measuring the degree of symmetry restoration in time starting from states which break the symmetry. Then you just change your operator, okay? And you get, you can look at the other one. So for example, if you look in the quantum case that we studied with Krysia, Mitya, and Oshin, it also shows it up, where now I change the operator to be the Hamiltonian as opposed to the magnetization. And also in the classical case, I apply the Fisher information story, and I also see it's there. So what all these Mpemba effects are a consequence of dynamical symmetry restoration starting from states which have different ordering and symmetry and can be understood through the resource theory of asymmetry and measured through the Wigner-Yanasi skew information. This is the point I want to make. With that, I'll conclude, take questions, and I want to say one thing since I'm in a different place. We have a position coming up in Dublin at assistant professor level, tenure track, covers all areas of quantum theory. And I know that probably there's many people that are really good postdocs in Brazil that might be interested in coming to us. And if you're interested, it's not yet advertised, just contact me, send me an email. Okay.
Questions? Gerardo has a question.
Rose from the dead.
So why you use the skew information in particular and not any of the family? Would it be special just for convenience, or it's something special?
No,
with this particular member?
Yeah, I mean, the only thing that we're thinking is that we want to extend numerics a little bit, and we're trying to come up with clever tricks within the tensor network framework to compute it, because again, it doesn't require this diagonalization of the instantaneous density matrix. But you're right, I think any of the generalized Fisher informations basically do the trick. Another advantage of Wigner-Yanasi skew information, along with the symmetric logarithmic derivative, is that the geodesic paths are known analytically, but we haven't explored that yet. But that's all. You're right. Anyone will do.
Thanks for the nice talk, John. And then you mentioned the U1 group, and this is a time translation symmetry group, and it's related to temperature in some sense. But if you, so all the thermodynamic relations are related to this group. And if you change this group, for example, to SU2 group, or
yeah.
what
So I didn't show here. We also have a circuit which is SU2 symmetric, and it works perfectly. The conserved quantity there is basically I mean, for example, the XXZ model at the isotropic point is SU2 symmetric, commutes with sort of SU2 operations, and you can break the symmetry in a number of different ways, but it shows perfectly well. Any symmetry will do.
Okay, but I'm asking this because of you.
The difference with SU2 symmetry, it's non-abelian, right? It is not charge don't commute, right?
Yeah. In the first part of the talk, you mentioned that you have a fixed point that relates to temperature for the Mpemba effect. This is fixed point has relation to the symmetry on the U1 group.
Okay, that's a good question. Maybe I wasn't explicitly clear. So in these closed system examples, you're really looking at a block of spins in an otherwise unitary dynamics. So, I mean, in the case of, say, generic ergodic systems, the belief is that if you take a sufficiently large system, the fixed point will be a sort of, it will be a sort of thermal state. But if you have a globally conserved charge, then you have, additional Lagrange multiplier, etc. But you can't. The point is that you can't actually. You can't. If you work in one dimension by Merman-Wagner theorem, you'll always restore a continuous symmetry that's broken, right, in the long time limit.
I see.
So it will always give you back a state with no symmetry at time infinity. Like, yeah.
I get it. Thank you very much.
More questions?
Thank you for this really cool talk. Now that you've related the Mpemba effect to the Wigner-Yanaz information, I was wondering, is there something that you could say about quantum speed limits for the Mpemba effect and the quantum to classical transition?
Absolutely, and this is what I was referring to Gerardo and Diogo's work. Actually, it's very easy, right? We were talking about it yesterday. Take any operator and look at its time derivative, right? I mean, you can always write that as a covariance. Let's say, for example, if you take the SLD, you can write that as a covariance between the fluctuations of A and the fluctuations of the symmetric logarithmic derivative. And you can derive a sort of Mendelssohn-Tam-like bound, generally speaking, for any dynamics, which is geometric and also classical, by the way, completely classical, geometrical. So I haven't thought about speed limits themselves here, but I think you're right, like that. I would need to talk to you guys, but the paper by Gerardo and Diogo go through the same procedure to derive speed limits. I think it's a very well-known paper. And more recently, it's kind of been extended in various different directions, actually, to similar concepts. So each of those Fisher informations in that continuous family identified by Petz produces a different bound. Often it's better to work with the SLD just because it seems to be tighter. But I saw recent work, I can't remember the guy's name, but which actually showed that there are certain cases where other members of the family can provide tighter bounds than the SLD. So I like this idea also of Fisher information with respect to time for the analysis of clocks, right? So a lot of people are interested in making clocks. We heard talks or people talking about time crystals, etc. And actually, if you take a kind of operational interpretation, you're really just giving you, it gives you an idea of sort of the precision in which you can measure time. So it's kind of, if you look at Eman's work, he has a body of work which is really nice. He actually has a resource theory of clocks, okay, which is a subset of resource theory of asymmetry for basically the symmetry, which is time translational symmetry. And he has this nice result, which is impossibility of coherence distillation of clocks, which relates to sort of all the monotones you get in this thing, and he uses the Fisher information for that. So there's a bunch of really interesting questions to ask in general, also for bounds from speed limits that are underexplored. Also classically.
More questions?
Have you thought about starting with entangled state? Will something change?
I mean, I don't know about this entanglement story. I mean, for dynamic, you mean like bipartite entangled?
So again, for quantum speed limits, it was shown that at least.
Because I mean, let me say something a bit, because I know you like to be controversial, but I mean, I'll tell you something, which in my mind is non-controversial. Bipartite entanglement for dynamics is completely uninteresting.
I see.
Because most states are entangled. And if you take many-body dynamics, after some time, you're at a volume law, and basically the probability that you get it's almost unit one, that you pick a state at random, the state is maximally entangled. Completely boring. Multipartite entanglement, on the other hand, is much more interesting, right? So There are some, so one open question is, we know how to link multipartite entanglement to Fisher information. Okay, this is known, how this is done. And we know how to link Fisher information for thermal states to linear response functions, so not too far away from equilibrium. But we don't know how to do it for highly non-equilibrium dynamics. So if somebody has a good idea, I think that's a great topic. But it's, as far as I know, nobody knows how to link to response functions very far away from equilibrium yet.
Thanks.
Okay, let's thank John again. Our next speaker is Diogo from NUSP. Okay, Diogo, thank you.
Hi, can you hear me? No? Huh? Now, can you hear me? Better? It's working? Okay, thank you. So I'll discuss in this presentation the idea of how this interaction between system and environment that are usually seen as a bad thing for quantum systems, how can we take some advantage related to this interaction? It's a couple of papers we've done recently. All of them is related to the postdoc of this young lady sitting here. And then basically the first work is related to the information flow and how the resources flow from the system to the environment and back in the sense of no Markovianity. And how can this information flow can be used to enhance precision. It's more or less an extension of a work from Gabriel Lange recently, a couple of years ago. So as we have some students in the audience, I'll try to give my talk in this way here. But remember always that it's just like this, and we are just in the very beginning. So I took this picture from the internet. I don't remember where I found it, but I found it so great, so I'm reproducing here. In the outline of the talk is I'll start with some notation, again, because of the students, just to be clear what I'm talking about. And then we're going to introduce the information flow and then enhance the precision thermometry. Though these are the papers we published, this is submitted. Well, just for notations, we have pure states, usually from textbooks of quantum mechanics, Cohen-Tanugier, and all these books, we have pure states, but these are vectors, and then we're gonna move it to matrices, the density matrices, which has these properties over here. And then we can also discuss the mixed states, where each of these vectors has a probability to occur, and then we have this definition of the density matrix for mixed states. And these are also the properties we need for the mixed state to have. Among the dynamics, whenever we know all the degrees of freedom of the system, you can access all the degrees of freedom of the system. We have unitary dynamics, and these are the properties of these operators that change your initial state to a final state. And we can have also the non-unitary dynamics. This is the scenario where we don't know, we don't have access to all the degrees of freedom of the system. This is the open system dynamics, basically, in terms of the Krauss operators with these properties. And among all the families of Krauss operators here, we can have this class, which we call unital dynamics, that maps the identity into the identity. This is the fixed point for these dynamics. Whenever I talk about zeros and ones, I'm talking about the sigma z basis here, and I'm gonna have this Pauli vector also using all the Pauli matrices. And the general initial state, then general state for a qubit, which will be our object of interest, will be written in this way here. And this will be the pure state version of the density matrix can be written in this form. And the mixed state version of the single qubit matrix can be written in this form. And just to check the purity of these states, because whenever you have the purity trace of square of O is 1. We have the pure state, and whenever it's less than 1, you have the mixed state. So you can map, using this structure, you can map the idea of the space of states from the mixed state or pure states into a sphere, which is known as the block sphere. On the border of the sphere, we have the pure states. Inside of the sphere, we have the mixed state for the single qubit. So also we're gonna see here lots about norms. And, we are thinking about the Schatten norms, the Schatten alpha norms, which has the generical form like this. And mostly we have the 1 norm, the 2 norm, the infinite norms. These are the norms we use along the works. Basically, norms in where most of the cases we are going to use A as a difference between 2 density operators, in the sense we are measuring distances or distinguishability of states of these 2 density operators, in the sense John was telling us before. In the information flow scenario, what we were studying was this. We have 1 qubit connected to 2 changes of qubits. And the first, this qubit we call the system is interacting with the first qubit of each chain. We have an interaction strength here for these guys, and between the qubits of the environment, we have another interaction strength. We can have this n up to n qubits on the environment. This is interesting because this model is experimentally friendly, because Thaisa, when she was doing her PhD, here with the guys from CBPF, they've done some experiments using a Damantan. And they model the Damantan just like this, the relaxation of the Damantan, exactly using this model. And the idea we want to discuss, we wanted when she came to the postdoc was, well, suppose that we can have some resource, some quantum resource here, and since we have a qubit, this resource will be coherence. And how, during the dynamics, due to this interaction, these interactions, how the dynamics will consume the resource, in the sense that the resource will be moving from the main system to the environment. And what will see, and since the environment is finite, how this, and in what sense this resource can flow back to the system. This was the idea, and then we were focusing on coherence, because coherence is the resource that we can have in a single qubit. Well, we know all the degrees of freedom of the system, and then we can map as a Hamiltonian the interaction between the main system to the first qubits in each chain of the environment, and the interaction between the chain, the elements of the chain of the environment is this one here. As I told you, this is something that is experimentally friendly. It's basically, you can find a sample in NMR that can be described using these 2 Hamiltonians. And the evolution of the total system is taking the exponential of these 2 Hamiltonians, and then we can evaluate the interaction and how the information is flowing from the system to the environment and back. Just to show, we have this initial state for the environment, for the system, sorry, and then we can start the system either on the plus state or on the minus state, and see how the evolution, how this information, the coherence, the maximum coherence for the qubit can be destroyed. We have also, in the very beginning, all the elements of the environment on the 0 state. And as always, as most of the cases, we start with the product state between system and environment. And this Hamiltonian is the sum of the 2 Hamiltonians I showed you before. And this is due to be the evolution of the whole system, you know. From this evolution, we will see that this coherence can be turned into these elements of the environment after some time. And then how we can do this from this total state, total evolved state, we can trace partial, we can do the partial trace and either have the information about the system or the information about the environment. And how can we distinguish what is going on, and how can we follow what's going on with the information on state? Basically, you have the normal one, the distinguishability between these 2 initial states, the evolution of these 2 different initial states of the system, and we can calculate the derivative of this Norm 1 is if it's monotonic, we have a Markovian channel. And if it violates this monotonicity, we can say that some information is flowing back to the system. Also, we can calculate the distinguishability of the states of the environment when we start with the system in the plus state or in the minus state, and see what happens with the environment during these dynamics. Also, we can have this derivative and learn about what is going on with the information. And this is what happens. It's interesting to see that this distinguishability measure starts in 1 here, which is a maximally distinguishable state, and it keeps going down until this value here. And if you see here, we started all of the guys in the environment going from 0 state to completely indistinguishable state to the maximal indistinguishable, to a maximal distinguishable state after the same time, same instant of time. And it's interesting when we saw this and that this plateau happening here, you try to understand what was going on in this system and thinking, because it sounds like all the information from the system is moving to the environment. But how can it go to the environment since we have a discrete environment? We see here that each of these lines, dashed lines here, are basically giving the information about the distinguishability of each of the qubits from the environment. And you see that the information start to grow, the coherence or the resources start to increase here, in the sense that we were fully indistinguishable to some distinguishability between the first guys on the environment. And the second guys do the same here, and the third in yellow, and the fourth in purple, and so on and so forth, as we had here. 7 possibilities, 7 elements of the environment. And each one was receiving its information and moving the information up to the last one here. The middle, sorry, the pointer is not pointing to the direction I want. So it's quite interesting, this pointer. Yes, the pointer points where he wants to point. It's totally independent of myself. Yes. I just release the laser and then he points to whatever. And so it's interesting because you see that after half of the plateau, in the half of amount of time of the plateau, the information went to the last qubit of the chain. And then it started to move back to the previous one and so on and so forth until more or less the same to be here in the first one, which if you sum all these guys, you're going to have exactly this shape. And it's interesting because in some point, all the information, almost all the information is going back to the system. It means that the system is again in a almost full distinguishable state. And the environment is almost in a fully indistinguishable state. This we were investigating to try to understand what is going on here. And we have some suggestion that this can be connected to the Darwinism. When the Darwinism appears here, in our sense, would be the discord going to 0. The discord goes almost to 0 in this point here. And then this is related to the environment elements become totally indistinguishable again. And then we see, if you look to the derivative, it's interesting because you see, it seems to be monotonically decreasing up to this point, and then it keeps 0 up to some point, and then it go back to, there is an information flow in this case here. More or less the same thing is happening with the environment. You see the two curves together. See the system and the environment losing and gaining information. So what we conclude about this paper was that we could measure, if you had the access to the degrees of freedom, you can measure, you can follow how the resources can move from your main system to each degree of freedom of the environment and back. And then thinking about this, Thaisa went to spend some time with Mauro in Belfast by that time. And then they were trying to think about it. Okay, it's known from Markovian scenarios, but how can we have some advantage? Can we think in a protocol that can have advantage for these scenarios? Can we use these ideas to regain information, to store information, to get information back, getting the information back to get some advantage in a quantum protocol? Then it comes to enhanced precision thermometry, which is based on some work of Gabriel Landi. He had done some years ago, where you have a system thermalized with an environment, and then your system interacts with some ancilla. The previous work just used a chain just like this, and then the interaction is just like the collisional model. And they have the advantage. Suppose that we have just this first line here, and you have the thermalization of your system with this environment, and then you have this collisional model. And after, you can thermalize again, and then you collide again, you thermalize again, and then you measure the ancilla and try to take the information from the ancilla about the temperature the system is encoded in the system from the environment. What have we done differently was this. We considered other layers of ancillas so that we interact with this ancilla, and one ancilla interact with another on another layer, and then this second layer ancilla interact back to the system. And how this interaction was done, it's mostly a kind of swap interaction. We need to take the information from the system to the ancilla, and from one ancilla to the other, and back to the system. The idea was that this swapping of information from one system to the ancilla could give the ancilla some information, and then we can estimate the temperature indexed in the system by the environment. And we wanted to see how can this improve the previous results, because you're going to spread the information about the temperature to this whole bunch of ancillas in different layers. And then the protocol we proposed is this one here. We have the thermalization of the system with the environment. Then we have the swap. It's not exactly a swap, it's a partial swap from the system to the first ancilla to the second one, and back to the system, and the second one to the third one, and back to the system. And then we want to measure these ancillas and estimate the temperature from these guys here. Just for you to have an idea, this is the thermalization of the system with the environment, and this is how the system and ancilla interact in a partial swap. You can do the partial swap controlling this coupling here. And then we have the ancilla interaction that can be done as a swap also, controlling this coupling here. And it's interesting to see, it was amazing to us. Oh, sorry, just one slide more. Is that to estimate the temperature, we go to the quantum Fisher information, and this information, and we can estimate this temperature by using the density matrices related to the ancillas. And since, as we've done in the previous work, we want to see how the information is moving from the main system to the environment, we can measure the distinguishability of all the states we have in between system and each ancilla in each layer, and then we can verify the distinguishability about the states to see how the states are being changed along the time. And then we can verify the monotonicity, because monotonicity is related to the information flowing from the system to the ancilla, and ancilla to the other, and back to the system, and we can see what's going on. And this is what happens for the distinguishability. All the information in ancilla is moving out the ancilla and coming to it's moving out the system and coming to the ancilla. And then moving to the first ancilla and going to the second ancilla. This is this distinguishability happening here. As we see the flux of information in this derivative here, the system losing information, the ancilla gaining information. How? The distinguishabilities, they are totally indistinguishable, going to the totally distinguishable, and moving just like this, and information is back to the system in blue here, coming back to the system. And if you go to the precision, this happens. This is quite interesting that if you have the quantum Fisher information of the ancillas versus the temperature, you see that the more layers we include, the higher the precision, the higher the Fisher information, more precise is your measurement. The former work from Gabriel's in workers is this dashed green line over here. So we are orders of magnitude higher now because we included more layers of ancillas. Because as we understood, the information being stored in these layers of ancillas, and then when we estimate, we are getting this information back. So this is another version of this maximum Fisher information as the number of ancillas. You see that you have is the estimation, the maximum, this peak here, in terms of the number of ancillas. And you see that if you increase the number of ancillas in each layer, you can have a higher peak of the quantum Fisher information. So and then we have also done the same with the chains, as you see here. So there is an improvement because we have these more layers since the information being stored in the extra degrees of freedom we have. So to conclude, and this is my daughter, and we see that usually we have this idea that the information flows from the system to the environment, and we lose the information. But if you have some protocol or some idea to control the information, a way to the information come back to the system, and we can have some improvement in the precision, and you can understand how the resources can be changed and moving from one to the other. Just one small comment that choose square root of choose because the World Cup was 2022. And then the same year we have the Nobel Prize in Physics for the Bell inequalities. And she wanted this Brazilian football team because she loves football. I don't know from who she took it because it's not from me. And then I decided I choose the number, which gave her lots of problem when she started to play football because no one understands this number. And what she always tells the guys in the football said, ask my father, he's a physicist, he's a crazy guy. So just to conclude, it's this couple of works were done in collaboration with these people here. Thaisa is the most responsible for all the calculations and interpretations and discussions because she understands all the stuffs, all the parts of these works. And it was supported by all these agencies. And then a special thanks for ENCT or Quantum Information that's about to finish now. And they supported our research for many years. And these are the papers, and I'm open to any question you may have. Thank you very much.
Questions?
Diogo, so have you checked, have you compared your final scheme with starting with a multi-party entangled state and just colliding with each one of the guys, or even a classically correlated state and colliding with?
It would be interesting to see how the role of correlations in the initial state would be interesting here. You mentioned correlations here.
Yeah, place the swaps that correlate.
I've never, no, didn't, but it's interesting.
Thank you for the talk, Diogo. I discussed this with Thaisa at USP. Just a clarification again on the protocol. When you have different layers of ancillas, so you measure the ancillas at the end. So when you have the various, your results, for example, for the Fisher information for the case, each of the curve refer to a single layer of ancilla. Yes, that is correct. Exactly. So you really see the information that is just accumulated on that layer of ancilla. Okay, thank you very much.
You're welcome.
Hey, Joe, good, thank you for the talk. Can you come back to the Discord plots for the system and the environment, please?
This one? Or the previous
no,
one?
Yeah, the crazy one with, yes. did you check taking like the mutual information for different fractions
Sure,
of the environment if you have like a classical plateau or something? I didn't understand this point.
Well, we checked it to understand this deep in here, and then we did it. But the classical correlation appeared just in this point here, the minimum discord we found close to this point here, and then we have discord along the plateau.
Thank you very much.
Hi, Diogo, nice talk. Just a curiosity, in this plot, the environment that you are considering has open boundary conditions.
Yep.
Okay, because I would think that if I have some information coming when I reach the borders, it gets back. So would you investigate something on what could be the effects of the boundary conditions on the environment?
No, but this is interesting to see. What's the condition, the boundary, what would be the importance of the boundary condition? For example, if it's not open, if you close in a ring, and then it's connected just like the central spin, and how the information will be turning around on the environment and see before coming back to the system. It would be interesting to see also.
More questions? We still have 5 minutes and Irene just disappeared, so.
Just one comment on this, because why we did not tested any other boundary conditions, Chris, is because it was a struggle with the computer to run all these codes and to survive the light being shut down in São Carlos from time to time. And then it took a month of calculation and a couple of shutdowns of light in the middle of one thing to the other. So in some point, it was impossible to run anything for long.
Okay, let's thank Diogo again.
This is the lightsaber. Just going from. You click twice, it moves
Twice.
Well, no, so if you click one, it goes forward. If you click two, go back. But the back button is this one.
Okay, so just click here to go forward and click to go back. That's so to remember.
And this is the pointer that points whatever he wants.
It's great.
Okay, let's go to the last speaker of the conference. So thank you, Irene, for being here.
Thank you, Thiago. So, okay, I have the honor and the onus to be the last speaker of the conference. Thank you, everybody, for being still here and still awake, at least for now. I'm Irene D'Amico. I will talk to you about something a bit different, a brief introduction about density functional theory, which, if anybody here knows about density functional theory, please don't listen. Will be really, really just to give a feeling for the people who don't know about density functional theory, of what are the bases and why, personally, I think this theory could be useful for quantum thermodynamics. And I will talk a bit about the uses I and co-worker have been doing so far for quantum thermodynamics. Before I move forward, I'd love to thank the organizer, in particular Thaisa, who have been extremely helpful to me since I was in São Carlos. She took care of me. And in general, to have this conference has been fantastic. John and everybody mentioned this, really fantastic conference. Please repeat. And yes, so I hope to be able to use this thing, which has tripped everybody else. So let's see. Yay. So following tradition, I'm telling you where York is. So this is where I usually live. It's true, he goes wherever he wants. And York is really a beautiful city, founded by the Romans, full of interesting buildings, the largest medieval cathedral in the north of Europe with the larger collection of stained glasses in England. Beautiful, fantastic. But we also have ghost and haunted pubs, Vikings, And there is a set of horrible history books about coming to York and be scared about all the spook histories about York. We also have piles and nails, which are very important to Steve. I don't see Steve at the moment. They said he loves the pie from Horton, England. And so this is probably why Constantine the Great, who was actually declared emperor in York, looks so relaxed in the statue we have in York. So if you haven't not done that, please come and visit. I'd love to guest you in York. And we go back to the talk. So why density functional theory? We have all listened and we all love to quite a few talks, and we've read a lot of articles about few qubit systems, often with no particle-particle interaction, and it's fantastic. We can also get analytical results from, for example, integrable systems. This is beautiful. We can learn a lot. I've also done work on this type of system. I've recently published a paper on a battery with 3 qubits, so that's good. I like it. However, if we look to real material, if we look at many qubits, if you look at including really particle-particle interaction, and we want maybe to measure quantities like entanglement or work or entropy that are really not observable quantity in the sense that they don't derive from as a mean value of an Hermitian operator, or we want to also do experimental measurement of system states, then we are a bit in trouble. Everything gets a bit more difficult. So I think these are the areas where indeed density functional theory could help. The idea in density functional theory is that with this idea of using density functional theory is that it could provide a way of writing these many-body non-local quantities like entanglement, work, and so on from local properties. So by this I mean we don't need to know about the wave function of the system, and we don't need to know if we are in an ensemble about the system state. Density functional theory can also provide a relatively good approximation to the many-body wave function or to the system state. I will make an example about that. But again, it's interesting the fact that within its scope, there may be the possibility, and I will give you some example, of actually writing expression for non-local or non-observable, in the sense I said before, quantities in terms of local quantities, in terms of usually local densities. And these local quantities are quantities that are actually measurable in experiments. So this is why I think, in a nutshell, density functional theory may be useful within the realm, not just of quantum thermodynamics, but in general, quantum information. Probably everybody knows of density functional theory as a ground state theory. In reality, there have been many, many extensions to density functional theory, to spin-dependent systems, to systems with time dependence, to lattice Hamiltonian. So we have DFT also for the Heisenberg Hamiltonian, for the Hubbard Hamiltonian, for the XXZ Hamiltonian. There is, people have started, not recently, but now it's coming back, working on thermal systems with density functional theory and on ensemble systems. It is used mainly, I would say, for equilibrium properties so far. It's one of the main theory to calculate properties of material, properties of nanostructure, you name the property, really. There are tons of reviews. There are very well-established public codes to calculate this type of properties. And it has indeed the ability of tackling very large many-body systems. There are a couple of papers I cited here in which was this one, which randomly goes, in which they actually work with millions of atoms. So there is a lot of power to it. The point is how to harvest. And in particular, this part here, so time-dependent system, lattice Hamiltonian, thermal system or ensemble or ensembles could be, I think, useful for QTD. So this is, as I said, a very, very high view of DFT flavors. We've gone paragliding. So just imagine you're looking from very, very top. So if you know anything about density functional theory, start and sleep, probably. No, don't sleep. I don't know, do something else, don't sleep. So all flavors of density functional theory are based on two things. The first is a Nonnemberg-Kohn type theorem. Nonnemberg-Kohn were the one who did the theorem for the ground state theory, then Runge-Gross for the time-dependent theory. Mermin did it for thermal DFT, etc., etc., etc. But we refer to them as Nonnemberg-Kohn-like theorems, and on a set of equations that are the practical way to solve the DFT and calculate properties, which goes under the name of Kohn-Sham equation, Kohn-Sham type equation. Kohn-Sham proposed it initially for the ground state system. And here I just listed a series of maybe my favorite books and review on DFT, but really Google DFT books or review. If you have never looked at density functional theory, I suggest this. It's actually published in the Brazilian Journal of Physics, but you find it on the archive by Klaus Capella. It's at UFABC currently. It's a really, really nice introduction, very simple to density functional theory. Nonnemberg-Kohn theorem, let me tell you what it says. I will talk about it for the ground state. Again, we have similar theorems for time-dependent, for lattice, DFT, for etc., etc. We have an Hamiltonian. I stay now with an electronic Hamiltonian, but would be a lattice Hamiltonian, as I said, where we have a kinetic term. We have an external potential, which is the sum of local potentials. That's important. And we have a many-body interaction. This is our Hamiltonian. It's actually a Schrödinger equation. And so what the Nonnemberg-Kohn theorem gives you is a one-to-one correspondence between, so for a given U, okay, for a given two-body interaction, it will give you a one-to-one correspondence between, in this case, the ground state local density, which is this object here. This is really weird. The external potential, that is this one, and the many-body ground state. Now notice this is a function of 3 variables. This is a function of 3 n variable. But what this tells you is that the many-body ground state and the many-body local density basically contain the same information. So the great thing is, if I get to know the ground state density, in principle, I know everything about the system. Okay, I know the ground state wave function. The implication is, if I have any functional, so in particular any operator, any mean value of an operator of my ground state, the theorem implies that this will be a functional of the density, of this ground state density. So I can skip the wave function. I can just calculate this directly from the density. Of course, it's an existence theorem. It doesn't give you the functional, but if you are clever enough to construct the functional or some approximation, you can skip the wave function. This is the power of it. Okay, Kohn-Sham system. So I told you the first ingredient of density functional theorem. The second ingredient, we have to calculate this density. Okay, so the second ingredient gives you a practical scheme to calculate the density of the many-body system, from which you can calculate everything else. Again, I'm talking here about ground state, but this can be similar theorem and similar scheme are there for all the other flavors. So we start from a many-body interactive system. For getting anything out of it, I would have to solve a many-body Schrödinger equation. If I have more than a few qubits, I start screaming. And However, what the Quantum theorem tells, the Quantum scheme tells you is that I can actually do something smarter and construct a fictitious system, is known as the Quantum system. This is a non-interacting system, but it has a great feature. The great feature is that its ground state density here is exactly the same as the ground state density of my original many-body system. So if I solve this system, I get my density. I can calculate the value, the mean value of my operators for the many-body interacting system. Basically, I don't even have to deal with the many-body system. Okay. The price, there is always a price. Somebody said it before, there is no free lunch. So the price is that when I write the Hamiltonian of the Quantum system, there is a term that appears in the potential, in what is now an external potential, and it's the so-called exchange correlation potential. This is a functional of the density, it's an unknown functional of the density. There are some properties, exact properties that are known, and by now there is a large number of approximations that people can use under different circumstances, under different flavors of DFT, in order to calculate the properties, and in many cases with very, very high accuracy. Okay, warning, warning. I say this because sometimes this is something people get confused on. So it's a repetition. What DFT promises you, if you add an exact exchange correlation potential, is to have the exact many-body local density. And if you have, it promises also that the observables are a functional of these local densities, and that you can use the local density in practice to calculate your many-body properties. And the local density are easier to calculate, to store, and measures. However, there is no promise on the wave function. So while many people use, I will also show you something about that, the Quantum system wave function as a wave function for the many-body system, there is no promise about that from DFT. However, often is also a good approximation. Okay, let's arrive to the QTD protocol I'm interested in and I will be discussing in this talk. So we start from finite temperature. We are in the canonical ensemble. We start from thermal equilibrium. It's a many-body system. We detach the system from the bath. We drive the system with unitary dynamics. I will work with a closed system. I arrive to a certain state, which is now out of equilibrium. If I want to relax back to equilibrium according to the new Hamiltonian h of t, I will have to attach my state to the bath, and I will have a dissipation. I will have some irreversibility coming into my cycle, and I will have production of heat, production of corresponding entropy, and so on. And finally, I have thermal equilibrium again. There is also a requirement for projective measurement, in this case, in the basis of initial and final Hamiltonian, if I want to calculate the production of work with the two measurement scheme. So from the point of view of many-body physics, this is a bit of a nightmare. I have many-body, I have finite temperature, out of equilibrium dynamics, I have irreversibility. So the point is, can we use DFT? Can we use it even to calculate non-local quantities, or irreversibility, or the fluctuation of the local quantities, and so on? So there are many question marks. As you can see, when I started looking at this problem, I start from a thermal state. Thermal DFT is not very well developed. What are the functionals? What are the approximations to be used? Similarly, if I look at the dynamics, I would have to use a thermal time-dependent density functional theory, which maybe is not even in its infancy. So I would have to think about something there. There is a requirement of projective measurements. How do I put this in the frame of density functional theory? What are the local densities that I have to take into consideration in all of this? I arrive finally at a reversibility, dissipation. What can I do in order to calculate these properties? which in general, again, are not operator in terms of quantities from DFT. I'm out of equilibrium. I can think of, it would be mixed states. Ensemble DFT is something they're trying to develop now. So there are a lot of incognita here. As I said, many quantities of interest are not observable. So I'm in uncharted territory for most of it. Which functional, which DFT functional? What are the dependency on the local density? What are the dependency of the density functional of, within all of this? Do I have workable approximation for the exchange correlation potential? Well, what we started doing for certain things is to demonstrate that certain quantum thermodynamic quantities are local density functional. We found that they were functional of which densities. We found some workable approximations. We computed the benchmark, and we found some new results. I will discuss this in the second part of the talk. But this is a bit the scheme that one would have to follow. And this is the outline of my talk after this introduction. I will first of all introduce the model very quickly that we have been using for our practical calculation and benchmarking. And I will give you three flavors in which you can think of using, or we have thought of using DFT within quantum thermodynamics. The first indeed uses the properties of the Cone-Sham Hamiltonian. What I told you that is not promised to you, that a Cone-Sham wave function or a Cone-Sham Hamiltonian is a good approximation for a many-body Hamiltonian wave function. But I will show you that it gives some good results under at least certain circumstances. Then I will briefly touch on entanglement versus average quantum work. Here we have been using T equals 0, so 0 temperature density functional. This is, Chris has given a beautiful talk on this part, on this work. It's a recent work. And in the third part, I will give you some flavor of our new results on actual quite rigorous derivation for thermal density functional theory and application to quantum thermodynamic properties in relation to closed quantum systems. So the many-body model we have been using for studying the problem, studying this type of method, is the one-dimensional fermionic Hubbard model. Has been already introduced. It's very nice. It allows for both itinerant electron and localized magnetic moments. It describes highly correlated system. It was started many years ago for condensed matter systems. Now it is used to describe, I don't know, chains of quantum dots, molecules, optical lattices with atoms, and so on and so forth. We will be looking for the exact diagonalization, and in general, we will be looking at finite chains with open boundary conditions. It's a complicated system. So each site has 4 states. 2 sites has already 16 states, 8 sites. You can see how badly scales. But if you don't believe me, that is a very complicated system. Let me show you this. So this is a 6-site part, not all of it, is part of the spectrum. The instantaneous spectrum, I have a time dependency here for the Hamiltonian of a 6-site Hubbard model. This is just the low midsection. And you can see I am increasing many-body interaction here. Here is still 0 interaction, relatively well behaved. You can see how messy it can become. So you have all sorts of crossing, anti-crossing, tons of state. So it is a complicated system. So when I say it's 6 sites, don't think it's just 6 sites, 6 states, or something like that. Okay, we are really dealing with a many-body system. Okay, so I started this business in relation to quantum thermodynamics a few years ago. These are the references. And now I will talk about approximation of the dynamics involved in a quantum thermodynamic cycle for the calculation of work using the Cone-Sham system. I will explain you in which way. So in this case, this is our Hamiltonian. I have a hopping term. I have a many-body interaction. The nice thing is that the Hubbard model has a lot of phase transitions. So in the thermodynamic limit, the many-body interaction drives the metal-to-mott insulator transition. You can see a precursor of this transition even in short chain, even in just a dimer, so just two sides. Then we have an external drive, which in this case is what we call a COM potential. So basically I start from states that are more or less with a similar, very similar local potential, and then I do this. So alternatively, I enhance or decrease the local potential in each site. And what this does drive a second type of transition. It's a Bantu insulator transition. This time again is driven by the external potential. These two transitions are in competition. This one is repulsive. The interactions would like to have half filling, one electron in each, would like to have single site occupation, so one electron in each site. This one, I am energetically making some of the sites really unfavorable, so favors double occupation. Clearly, I have a competition. So I can do exact results, exact diagonalizations, and these are for L equals 6. This, I think, was done by Ami Skelt or maybe by Christian numerically. And this is the extracted work. This is the time it takes to do the, these are finite time processes. And this is the many-body interaction increases. So here I have a sudden quench regime. Here I have an adiabatic regime. Here I have increasing many-body interactions, which means that I have a precursor to the metal-to-mott insulator transition. You can see your system is freezing. I can produce less and less work. Here I have an early onset of adiabatic regime, and up here I will have a competition between Mott insulator transition and band insulator transition. So it's a complex landscape for the extracted work. These are the exact results. We did a calculation also for increasing temperature. And the approximation we did here for calculating the dynamics, because again, the problem is, you can see in this case, the big problem is really calculating the dynamics of my system, is a many-body system, is to consider to approximate the evolution Hamiltonian here, which should be the full Hamiltonian, with the Kohn-Sham Hamiltonian, okay? This is a ground state Kohn-Sham Hamiltonian. This is the single particle external potential is time dependent. We even did something worse than that, because we could have chosen, and we did later on, an exchange correlation potential which would also be time dependent, but in this case, for the results I will show you, is static. And so the R3 potential is also static. And you can think of this as a zero-order perturbative approximation. So I can write my HT as H Kohn-Sham plus a certain perturbation. I take the zero order, I throw away my perturbation, okay? In this sense, I could have higher order, and I can apply the system, this to higher, to large system. So I will just show you one of the approximation proposed in this case. This is the one in which we start, we assume that we can calculate very well our initial state. So in particular, we use the exact initial state, which means we are introducing correlation in two ways, through the Kohn-Sham potential in the evolution, but also through the initial state, okay, at time equals 0. And what we find, and yeah, we have done this calculation with different, increasing more accurate exchange correlation potentials. And what we find is that indeed, so these are the exact results. These are the results in which I actually consider a non-interacting Hamiltonian. These are my benchmark results for, instead of the Kohn-Sham Hamiltonian, for the evolution. And these are the results from two approximations of the constant potential. This is the more accurate within this approximation, and we find that indeed we reproduce qualitatively quite well in all ways, except I would say for the Balda at high correlation, the exact result. If we look at them quantitatively and with respect to temperature, this is the red is the more accurate. So where there is a color, it means that that approximation is the best for that particular regime. Red is the case in which I have an exact ground state exchange correlation potential. You can see that this is important at high correlation, and this is sudden quench. But very interestingly, the green is where the non-interacting approximation does well. What you see is that when we go up in temperature, so from here to here, really we would need a density functional that accounts for thermal effect in order to improve. Second way of using density functional theory, we did this in relation to quantum work with the T equals 0, temperature equals 0 formalism. This is the paper. And again, Chrissy already discussed this paper, so I will just say a few words. In the group of Vivian Franza, they consider the superfluid to insulator transition. This is an Hubbard model with attractive interaction. And they found that by varying the concentration of impurity on the Hubbard model, there is a very clear signature of the transition with the entanglement. This calculation was done already using density functional theory. This is a chain of 100 sites, so definitely you cannot diagonalize it directly, but there is a functional for calculating for the Hubbard model the site entanglement. And also, they then use the parametrization that Vivian and I did in order then to practically calculate this functional. And then what we did with the work, we, at 0 temperature, tried to characterize the same transition with sudden quenches. And we found, indeed, that at the transition, we have to inject a large amount of energy, if you like, so a large amount of work in the system. And this is also done with the FT calculations. And this gave us the possibility then to have the signature and then look at a smaller chain and check how the signature of the transition would decrease with temperature. At this time, we didn't have the FT functional for higher moment, even at T equals 0, so we couldn't analyze the higher moment of the work distribution with the FT, nor the FT functionals beyond temperature equals 0. The rest of the story have already been given by Christia, so I will move to the last part of my talk that is related to deriving thermal DFT for closed quantum systems, specifically for some of the quantum thermodynamic properties of interest. This is the paper, is going to be published very soon. We are with the proof on PRA, and this is the star of the paper. This is Antonio Palamara, who came to visit my group because he wanted to do this type of stuff. And so this led to the collaboration also with Francesco Plastina and Antonello Sindona. So the idea here is to express, remember, we don't even know if this quantity when we started could be expressed in terms of local densities, if they were functional of local densities. So first of all, we need to check if we can express this quantity in principle as functional of thermal equilibrium density. We are now in thermal equilibrium, so thermal equilibrium density. We have to consider finite temperature approximation for the functional, find something. We will have to benchmark and possibly give you some new results. So this is the Mermin-Koncham theorem for closed quantum system. This is my Hamiltonian, and in particular, I have an Hamiltonian with local potentials here, and this lambda I are the parameter I can turn in my lab in order to change my local potential. My state, this is thermal, this is equilibrium, so it's a Gibbs state. This is the partition function. And I can define a generalized equilibrium density in this way. So simply tracing, taking the trace of my local potential with the state of the system. And what the Mermin-Cauchy theorem demonstrates is that if I know these densities, I know the parameter, and I know the state. So again, one-to-one correspondence. So if I can get this object, I can get the rest. Okay, so I will just enunciate a few results. A bit has been rewriting on results that were already on the literature. A bit has been in the framework of of our interest. A bit has been rederiving. So first of all, the free energy. Indeed, if I think about the free energy, I can see immediately that I can write it as a trace of a functional, if you want, so already a functional of my state. And this tells me that because of, I wanted to go back, because of the Mermin theorem, I can also write it as a functional of my local densities, generalized densities. So first result. Now, this is formal. This is a universal functional. By universal, I mean doesn't depend by the local potential. Generally unknown, you have to look at your problem. And this is explicitly dependent on the density and also parametrically on your parameters. What is interesting is that if you now apply the Hellman-Feynman theorem, what you discover is that actually a way to obtain your generalized density is to consider the derivative of your free energy with respect to the lambda E, or vice versa. So you find this very interesting connection between the key quantity of density functional theory and your free energy. Probability distribution for the work. Okay, this is not an observable. So can I write it in terms of local density? Can I not? Let's see. To do this, we look at the characteristic function, basically the Fourier transform of the work probability distribution. Here it is. These are the moments of my work probability distribution. If I go to the sudden quench, again, I can write this quantity here as the trace of some operator with the exponentials of operator with the state of the system that I had initially. So again, because of the Mermin system, I know formally that I can write it in terms of my generalized densities. And similarly, I can do the same for any moment of my probability distribution for the work. So I know that indeed, once I find the functional explicitly, I can calculate these objects through density functional theory, no matter how complicated is the system, once I have the functionals. You can see here that there is a parametric dependence for the moments on the initial and final parameters for my potential. It's parametric. And this is, if you want to tell you, is a leftover from the fact that you are actually measuring, if you like, in two bases, at the beginning and at the end. But what is interesting is that because it's a sudden quench, it's just a function of the initial generalized densities. So again, PW can be calculated to thermal DFT. Then we can find some explicit functionals for, at least for the first two moments. Average work, this is the same functional we have also used in the calculation with Vivian, Guilherme, and Crissia for the work just shown before. And if we have an infinitesimal sudden quench, we can also express the width of our distribution as a functional of our generalized density. And we can actually separate it in a part that contains the commutative part, if you want, of your Hamiltonian. So if your final Hamiltonian commutes with your initial Hamiltonian, I have this explicit form for the second moment of the distribution. that I can calculate again from my density, my local density. If it doesn't commute, I have this additional term, which has, we describe in the paper how to calculate this. So there is a way of calculating it, but it's interesting that we can separate it in this way, and you can see this in the functional itself. Irreversible entropy, another quantity that God knows if we could or not calculate through density functional theory. So the irreversible work is the difference between my work and the work I would get at equilibrium protocol in equilibrium with the bath. This never happened for a closed system, so I define an irreversible entropy. And this is associated to the relaxation process of my final state to the equilibrium at the end when I connect to my bath. And from previous consideration, because both the first moment and the free energy are I can write them as functional of my generalized density, I know that I can do the same for the irreversible entropy, again, something that was not a given. And for an infinitesimal sudden quench, again, I have an explicit formula for it. So some result we want to benchmark. So we go back to the inhomogeneous subbar model. We go back, we will consider both of these potential. This is the one we have seen before, and this is the one in which we start from a local potential like this along the chain, and we tilt it. The functional we have used is an LDA type of functional, is the exact finite temperature upper single site artery exchange correlation potential for whoever is in the known. And these are the results. So these are the exact results for the extracted work and for the irreversible entropy. I talked before about the competition between two-phase transition. Here you can see them very clearly. Here you have your band insulator. This is the initial difference between the sites, the nearby sites of my model here. This is twice U naught, and U is the on-site, it's in the off-site repulsion between the electron. So in the regime of band insulator, this is high. I can extract more work. In the regime of Mott insulator, I cannot extract work. Basically, my system freezes. In the middle, I have the transition, I have a kind of metallic phase. And it's really a line corresponding to the case in which the Coulomb interaction and the potential here, a difference in potential barrier equilibrate. What is nice is that if I look at the reversible entropy, this very clearly show the transition. And these are the results for thermal BFT. They are basically indistinguishable up to 4 significant figures. So what is nice, because before we had the problem, we find the problem at high correlation, we find really good result by applying density functional theory properly, even in the case of high correlation. Here I arrive at U equal 10, U equal J is the same value I arrived before in the other plot, but you could see that in the other plot, when I arrived to high correlation, we had problem by using the DFT. I'm almost there. We check now with something bigger. So we check with chains up to an L equal 8 sites. These are the local density, our ingredients, the exact and the consham. You can see that the results are very good. This is the type of potential, is the one that gets tilted. And so we do some results also on the work. We check that also with our functional, the average work against the benchmark works well. This is for increasing value of V naught here. And you can see that again, we get very good results for all values of U. And finally, we can get some new results. These are the new results. So these are now long chains. These you cannot diagonalize exactly. This is L equal 16. This is L equal 20. Here we have the slope potential. So the potential that goes from here to here with the sudden quench. This is the harmonic potential. So I have a parabola. This is my chain confined with a parabola. I have a confining potential. And I open it as a sudden quench. And what is interesting is that in the Mott insulator phase, when I have a slope potential, I have the least extractable work. But when I go to my parabola,
what I find is that in the same phase, I have the most extractable work. So I can see that depending on my confining potential, I can get work out of the MOT phase, and vice versa, because this is the band insulator phase. Which brings me to acknowledge my collaborators. So these are my Brazilian collaborators that have worked with me on this work since many years, all these works, I mean, since many years. Ami was my student, and now she works in a company, but still work also in research, and a good part of the results on the quantum system are due to her. Marcela is now in Colombia, faculty in Colombia, and this is the new, well, new in the sense it's the last paper I showed you, the new results. This is the thermal DFT collaboration. All the three of them, Francesca, Antonello, and Antonio, are in the University of Calabria, which brings me to the final conclusions. I showed you how you can use concepts from DFT, in particular the quantum Hamiltonian and somewhat the quantum state, to derive good approximation for complex dynamics of many-body system. We got good approximation in a good set of parameters. I showed you a way in which we calculated entanglement, well, in this case, Vivian calculated entanglement, and we calculated the average work at the superfluid insulator transition using density functional theory. And then I showed you our recent progress in thermal DFT in both defining, checking if actually the quantity of interest for quantum DFT can be considered functional of local densities, finding this functional, and finding viable approximation for the exchange correlation potential for actually doing calculation. Thank you very much for your attention. That's it.
Questions?
Thanks for a nice talk. I know nothing about DFT, but I mean, so one of the things I was wondering, in connection to the last part of the talk with the Calabresi, I know them as well, but so you know, in this sort of story of work statistics and many-body physics, you know, like for quenches or whatever, I mean, almost always we exclusively work in the canonical ensemble. Like you assume at thermal initial state, that's Gibbs form. But work statistics actually can be formulated as well for the microcanonical ensemble. So I mean, it's just not applied to the many-body case usually, but there's really nice formula. It requires you to know stuff like the density of states. I was wondering, is in DFT, is there any work done on microcanonical?
So there is
DFT?
a lot. Usually, what is used is the grand canonical, because you have large number of particles, and so fluctuation don't really matter. They do it really for a fixed number of particles. The fluctuations are so small, then don't matter. We were the first doing this stuff with canonical ensemble. There are technicalities which I will not go into detail, but yeah, I think it could be done. It's just a matter of sitting down and checking the theorem and checking, which is what we have done in this case. So in principle, I think yes.
Yeah, I mean, because like it really, nobody kind of studies it for many-body physics, but it is a complete formalism.
Yeah, I mean, in principle, yes, it's a matter of checking all the things, but this time for the microcanonical ensemble, and in principle, yeah, there's no
questions.
Hi, Denny. Thanks for the talk. Regarding our final results of work extraction, entropy production, so on, can you estimate the deviation from the exact solution as a function, how it scales with the size?
We haven't done we have done a benchmark of sorry, I am going where I should not. These are the slides that there's some 60 slides that are there because I didn't cancel them. So no, I don't have a trend. We have estimated for up to where we could do exact diagonalization. So we arrived to L equal 8, and we checked that the deviation we are very, very small, of the order of a few percent. Yeah, this is done, by the way, with the we were a bit surprised with the fairly, I mean, checking all the things, but this time for the microcanonical ensemble, I don't want to say naive, but almost exchange correlation potential, because this is simply guaranteeing you that in the type of exchange correlation potential is the one that guarantees you that in the high correlation regime, is the one that is done to have the exact exchange correlation potential for the single site. And we have simply taken that there. And that's the only exchange correlation we have inside. So the results could even be improved by using other type of exchange correlation potential. Already with that, we were very surprised. We got extremely good results. But we can do the trend up to when we can solve analytically. So we have numerically, don't solve this stuff analytically. And in general, I can say that DFT so far in other fields have been very, very good once you have a good function, the exchange correlation function.
More questions? Okay, if not, let's thank Irene again. So you managed to end it. So I think Eva is gonna make some closing remarks.
Well, here we are on Friday lunchtime. In the name of CBPF, I would like very much to thank you all for your presence and for the fantastic week we had. I hope you will have enjoyed that. And I would like also to thank our sponsors, which are basically CNPq, INCT, which is CNPq on the back, well, CBPF, and also the American Air Force for the cold beer, which was very nice. So I want to especially to thank Thaisa and Thiago for the hard work they put to make to have, and Fernando too. Yeah, Yamini. He's the chairman too. So let us thank them. Go back home safe and come back soon. Obrigado.